There is a world under your feet that is stranger than space itself. It is a secret place of crushing pressures, searing heat, and metals swirling like a cosmic engine. You'd have to go 4,000 miles down into the Earth, past moving tectonic plates and rivers of solid rock that move like liquid. At the bottom, you'd find an iron heart that is hotter than the sun's surface. People will never reach that faraway place, but its unseen forces affect every part of our lives, from the way the continents move above us to the magnetic shield that keeps all living things safe from space's deadly winds. The descent begins, from crust to mantle. When you stand on the ground, you might realize that what you think is solid is actually just the surface of a much more complicated world. The material we live on, called the crust, is surprisingly thin compared to the rest of the world. It's like an eggshell, very thin. But just a few miles below, the weather changes so drastically that it feels like you've entered a different world. To get to the next part of the trip, the first step is to break through the crust and enter the mantle, which is not at all like the land we know. The crust itself is not uniform. Under the oceans, it is usually just about 3 to 6 miles thick, made mostly of basalt, a dark volcanic rock. Under continents, it thickens to around 20 to 40 miles, built from granite and other lighter materials. But either way, when you compare it to Earth's total radius, about 4,000 miles, it's like a paper-thin coating. That's why geologists often say we've barely scratched the surface, even with our deepest mines and drills. The Kola super-deep borehole in Russia, the deepest artificial hole ever drilled, only reached 7.5 miles, just 0.2% of the way to the core. Even there, temperatures were far hotter and pressures far greater than scientists had expected. What lies below this thin crust is the mantle, which makes up about 84% of Earth's total volume. It's not molten rock in the way many people imagine. Instead, it's solid rock that behaves strangely. It can flow very slowly, almost like putty, over long time scales. This is the region that powers earthquakes, volcanoes, and the drift of continents. When a tectonic plate dives down into the Earth at a subduction zone, it's not disappearing. It's sinking into the mantle, carrying with it water, carbon, and chemical fingerprints of life from the surface. Crossing from the crust to the mantle is like walking through a hidden door in Earth's architecture. Scientists know this boundary exists because of earthquakes. When seismic waves, vibrations from a quake, travel through Earth, they change speed suddenly at this layer, as if they're hitting a different kind of material. That sharp boundary is the first sign that the crust has ended and something else has begun. Later chapters will dive into this in detail, but it's important to note here, without earthquakes, we would have almost no idea what lies beneath. The mantle is not just one endless zone of dull rock. In fact, the very top of the mantle interacts with the crust in dramatic ways. Hot material rising from the mantle can thin and break the crust, forming rift valleys like the East African Rift, or ocean ridges where new seafloor is born. On the flip side, cold, dense slabs of old ocean crust sink back down into the mantle, stirring it like giant spoons. This constant recycling keeps Earth geologically alive, unlike Mars or the Moon, whose interiors have mostly gone still. New findings show that even the upper mantle has secrets to offer. Under very high pressure, diamonds form, which are some of the hardest and rarest things on Earth. Minerals from hundreds of miles below the surface have been found in tiny flaws inside diamonds. This is clear proof of what the mantle is made of. Even stranger, some diamonds have tiny water drops inside them, which means the deep Earth may be wetter than we thought. If this is true, this secret reserve could hold as much water as, or even more than, all the oceans at sea level. Drilling into the mantle has long been a dream of geologists. In the 1960s, the US launched Project Moho, an attempt to drill through the ocean crust into the mantle, since oceanic crust is thinner. The project was cancelled due to cost, but modern scientists still chase the goal. Japan's drilling ship Chikyu has come closest, boring into the seafloor in an attempt to pierce the crust-mantle boundary. The challenge is not just depth, but temperature. Rocks get so hot they can melt the drill bits, and pressure which squeezes everything with crushing force. Crossing from crust to mantle also reveals how Earth's composition changes. The crust is rich in lighter elements like silicon, aluminum, and oxygen, but the mantle is dominated by heavier minerals like olivine and peridotite, greenish rocks that rarely appear at the surface unless dragged up by volcanic eruptions. These minerals not only withstand extreme conditions, but also behave strangely under them, transforming into new structures at different depths. For instance, olivine morphs into wadsleyite and ringwoodite deeper down, minerals that don't exist at the surface but tell scientists about pressures and conditions far beneath us. The Mohorovicic discontinuity. It was 1909 when a Croatian seismologist named Andrija Mohorovicic found something that changed the way we see the inside of Earth forever. He carefully watched how earthquake waves moved through the Earth and noticed something strange. Some waves sped up all of a sudden at a certain depth below the surface, as if they had hit a new kind of material. The clear line between Earth's crust and core is marked by what is now known as the Mohorovicic discontinuity, or just the Moho. The Moho is one of the most important signs to knowing how Earth is made up of layers, even though no one has ever been there. The Moho is not at the same depth everywhere. Under the ocean floors, where the crust is thinner, the Moho lies only about 3 to 6 miles beneath the surface. But under the continents, where the crust is thicker, it can sink as deep as 20 to 40 miles. This means if you drilled straight down through ocean crust, you'd reach the Moho much sooner than if you drilled through continental crust. Yet, despite being close, in geological terms, no drill has ever touched it. Every attempt so far has been stopped by the incredible heat, crushing pressure, and mechanical challenges of boring into solid rock that gets tougher the deeper you go. What's intriguing about the Moho is how clear the earthquake-proof is. Two main types of waves are made when the Earth shakes: P waves, which are compressional waves like sound waves, and S waves, which are shear waves that move back and forth. They both move at different speeds based on what they're going through. Mohorovicic noticed that some of the seismic waves that were picked up by tracking stations had moved faster than expected. The only thing that could have caused it was that they had gone below the crust to a thicker layer where the rocks are harder and waves travel faster. This was the first strong proof that the inside of Earth is not flat, but stacked. Scientists now know that the Moho represents a sharp change in composition. Above it, the crust is made mostly of lighter rocks, granite on continents, basalt under oceans. Below it, the mantle begins, dominated by denser minerals like olivine and pyroxene. This switch in rock type explains why seismic waves suddenly accelerate. The mantle's minerals pack together more tightly, allowing vibrations to move faster. In essence, the Moho is like the dividing line between the Earth's outer skin and its deeper muscles. For years, scientists thought the Moho was just a clean, sharp boundary everywhere. Recent research, however, suggests it can be more complex. In some places, seismic studies hint that the Moho isn't a single surface at all, but a fuzzy transition zone a few miles thick. This suggests that processes like partial melting, chemical mixing, and even water trapped deep in the crust might blur the line between crust and mantle. In other words, the Moho might look neat in textbooks, but in reality it can be messy, varying from place to place. Finding out how the Moho is connected to Earth's water is one of the biggest secrets about it. Some research on rocks from volcanoes close to the Moho has shown that they have more water than expected stored in minerals. This means that the Moho might act as a water filter, showing where ocean rock that has been pushed down into the mantle lets its water out. Water like that drops the temperature at which rocks melt and helps volcanoes erupt at the top. The Moho isn't just an inactive line in this way. It may also affect earthquakes, volcanoes, and the recycling of Earth's surface materials. Studies of earthquakes in areas that are prone to them have led to another unusual discovery. It looks like the Moho is sometimes twisted, bent, or even cracked where there are earthquake lines, like in California or Japan. This proves that the crust and mantle are not always rigidly different layers. It can be pushed or pulled up by geological forces, which change its shape over millions of years. These changes can even make ways for magma to rise, connecting processes in the deep core to volcanism on the surface. Geophysicists have also discovered that the Moho holds clues about continental formation. Ancient continental crust, billions of years old, often has a deeper and more stable Moho compared to younger regions. By mapping the Moho's depth across continents, scientists can trace the hidden roots of ancient landmasses, piecing together how continents grew and collided in Earth's past. In a sense, the Moho is like a fossil record, but instead of bones, it preserves the architecture of Earth's building blocks. The mantle's slow rivers. We think of rivers as bodies of water that run across land. That being said, there are rivers inside Earth that are not made of water but of solid rock. The mantle is about 1,800 miles deep and starts just below the crust. For now, it looks like it will stay solid. You could hold a piece of it in your hand and feel how hard and firm it is. But over millions of years, this solid rock has flowed like thick honey under a lot of heat and pressure. Oceans, volcanoes, and the moving of continents are all caused by these slow rivers in the core. The flow of mantle rock is called convection, and it happens because heat from the deep Earth is constantly trying to escape toward the surface. When rock is heated at the bottom of the mantle, it becomes slightly less dense and rises upward. When it cools near the top, it sinks again. This cycle is similar to the way boiling water circulates in a pot, except it's happening in solid rock across thousands of miles. These convecting motions are unimaginably slow. Rocks may creep upward or downward only a few inches per year, but over millions of years, they reshape the entire planet. The effects of mantle convection are visible at the surface. When hot mantle material rises, it can split continents apart and create new ocean basins. This is what drives seafloor spreading at places like the Mid-Atlantic Ridge, where new crust forms as magma wells up from below. When cooler, denser mantle sinks, it drags oceanic crust down with it in subduction zones, such as the Pacific Ring of Fire. This recycling of Earth's surface is the reason we have plate tectonics, earthquakes, and volcanoes. Without the slow rivers of the mantle, Earth's surface would be geologically dead, like the Moon. For decades, scientists pictured mantle convection as simple cells, with one rising column of hot rock and one sinking column of cooler rock. But seismic imaging has revealed that it's far more complicated. Instead of neat, simple patterns, the mantle is a chaotic, ever-changing network of currents. Some rising plumes are thin and narrow, like the one that fuels Hawaii's volcanoes. Others are massive and broad, spreading out under continents. Likewise, slabs of sinking ocean crust sometimes plunge all the way to the bottom of the mantle, while others stall midway, creating traffic jams of rock deep underground. It was a big surprise to learn that mantle flow changes as you go deeper. The skin is not a single layer that is all the same. High pressures push rocks into new crystal forms 400 to 650 miles below the surface. This is the transition zone. This zone can slow down or change the path of the mantle's slow rivers, like a speed bump. Some rising plumes of hot rock get through and power volcanism on the surface, while others flatten out and spread out to the sides because they can't get past this barrier. Similarly, pieces of crust that are sinking may stop here and pile up before they finally drop deeper. Some places on Earth have active volcanoes while others don't. This secret choke point in the mantle may help explain this. New research also suggests that the slow rivers in the mantle may carry a lot more than just heat. They may also carry huge amounts of water and carbon. Minerals and water that are stuck in the mantle are dragged down by the ocean plates as they sink. These things can go hundreds of miles underground before they come back up. Some of this water makes subsurface rocks melt at lower temperatures, which helps volcanoes erupt more quickly at the surface. Volcanic events release some carbon back into the air, ending the deep carbon cycle that helps keep Earth's temperature stable over millions of years. The mantle stores and reuses the basic building blocks of life in this way, acting like a secret reserve. The connection between thermal flow and Earth's magnetic field is another interesting thing about it. The magnetic field is made in the outer core of liquid, but the layer above it controls the flow of heat that moves the core. Through slow rivers in the mantle, the amount of heat that leaves the core is controlled. If mantle convection slowed down a lot, it could change how the core works, which would weaken the magnetic field that protects Earth from dangerous sun radiation. This means that the mantle is not only a natural engine, but also a system that keeps life on Earth going. The transition zone, a hidden reservoir. Between about 250 and 400 miles beneath our feet lies one of Earth's most mysterious regions, the mantle transition zone. It's not a place we can see or touch, but seismic studies and high-pressure experiments reveal that this hidden layer may hold more surprises than almost any other part of the planet. For decades, scientists thought of it as nothing more than a mineral boundary, a middle ground between the upper and lower mantle. But recent findings suggest it could be a vast reservoir, possibly containing more water than all of Earth's oceans combined. The transition zone exists because minerals change their structure under extreme pressures. At the surface, the mantle's dominant mineral is olivine, a green crystal also found in volcanic rocks. But as pressures increase with depth, olivine transforms into new, denser minerals. Around 250 miles down, it changes into wadsleyite, and deeper still, into ringwoodite. These minerals don't exist naturally at Earth's surface. They collapse back into olivine when brought up. But deep inside Earth, they make up a significant portion of the mantle. What makes wadsleyite and ringwoodite so special is their ability to trap water. Not liquid water like oceans or lakes, but water locked away inside their crystal structures in the form of hydroxyl ions. Laboratory experiments show that these minerals can store several % of their weight in water. That may not sound like much, but spread across the vast volume of the transition zone, it adds up to an enormous hidden ocean. Some estimates suggest it could equal or even exceed the volume of all surface water combined. The first hard evidence for this came in 2014, when a tiny diamond was discovered in Brazil. Trapped inside was a microscopic grain of ringwoodite. When scientists analyzed it, they found it contained water, direct proof that the transition zone is not dry. This discovery confirmed what seismologists had long suspected, that parts of Earth's interior are much wetter than expected. It changes how we think about the deep Earth if the transition zone is really a huge water tank. Water drops the temperature at which rocks melt, which makes it easier for them to make magma. In this way, the transition zone might have the power to control where and how volcanoes explode on the surface. It could also explain why some volcanic hotspots, like those in Hawaii or Iceland, make magmas that are very high in water. Deep storage in the transition zone could be letting water leak up. The presence of water here also affects how the mantle convects. Water makes rocks weaker and more ductile, allowing them to flow more easily. If the transition zone is wetter in some places than others, it could speed up mantle flow beneath certain regions, stirring the planet unevenly. This may help explain why some parts of Earth's surface are volcanically hyperactive, while others remain quiet for millions of years. The transition zone also acts as a kind of traffic controller for tectonic plates. When slabs of ocean crust sink into the mantle at subduction zones, some plunge straight through the transition zone into the lower mantle. Others get stuck and flatten out, piling up like wrecks on a highway. This slab graveyard effect may be tied to the mineral changes happening in this depth range. The olivine to ringwoodite transformation makes rocks denser, encouraging slabs to sink, but the next transition, ringwoodite into even denser bridgemanite in the lower mantle, creates a buoyant effect that resists further descent. The result is a complex balance that sometimes stalls slabs for millions of years before they break through. Seismic imaging has also revealed patches of unusual behavior within the transition zone. In some areas, seismic waves slow down dramatically, suggesting the presence of partial melt. These melt ponds may be fueled by water released from sinking slabs, which causes rock to melt more easily. Such hidden magma pockets could explain the origins of some of the most powerful volcanic eruptions in Earth's history. Scientists use big lasers and diamond anvil cells to study the transition zone. These tools can squeeze small pieces of rock to the same pressures that are hundreds of miles below the ground. These tests show how rocks like ringwoodite act and how much water they can hold. When put together with earthquake studies, they give a picture of a layer that is always changing and full of water that is very important to Earth's engine. The slab graveyard. Beneath our feet, Earth is not a still or silent planet. It is alive with motion, driven by the relentless recycling of its outer shell. At the surface, continents drift and collide, oceans open and close, and mountains rise and erode. But the real drama lies deeper down, in the mantle, where giant fragments of Earth's crust, the remnants of ancient tectonic plates, are swallowed into the depths. These slabs don't vanish when they sink. Instead, they pile up in what scientists call the slab graveyard, a hidden underworld where old ocean floors go to rest. By listening to how earthquake waves travel through Earth, scientists discovered cold, dense zones deep in the mantle. These anomalies didn't match the surrounding hot rock, and their shapes looked suspiciously like giant plates of crust plunging downward. Over time, researchers realized they were seeing the ghosts of entire tectonic plates, preserved hundreds, even thousands of miles below the surface. Most slabs begin their journey at subduction zones, the deep-sea trenches where one tectonic plate dives beneath another. As the ocean crust sinks, it carries with it sediments, water, and even the chemical fingerprints of ancient life. These slabs are colder and denser than the surrounding mantle, so they sink like stone into water. But their fate isn't simple. Some slabs plunge straight through the mantle into its lower depths. Others stall in the transition zone, around 400 to 650 miles down, stacking up like traffic jams. Still others fold, twist, or break apart under immense pressures. The slab graveyard is not uniform. In some regions, slabs seem to accumulate at the bottom of the mantle, just above the liquid outer core. There, they may rest for hundreds of millions of years, preserved as cold patches in a sea of hotter rock. In other places, slabs appear shredded, mixed into the mantle flow, or partially melted into strange anomalies called ultra-low velocity zones. The variety of slab behavior suggests that the mantle is not just one big conveyor belt, but a chaotic, ever-changing engine with multiple layers of circulation. It would be good to know if these slabs reach the very bottom of the mantle and pile up where the core meets the mantle. There are studies that use seismic waves that show thick curtains of cold rock going down almost 1,800 miles from tunnels on the surface. These slabs have been storing the past of plate tectonics for billions of years, if what they say is true. These underground slabs might even be able to hold things in place and change where hot plumes rise from the core. Some experts think that the site of big volcanic events in Earth's past, like the eruption that made the Deccan Traps in India, was caused by old slabs that changed the flow of mantle. Slabs also carry with them some of Earth's most precious cargo, water and carbon. As they sink, they drag down hydrated minerals and carbon-rich sediments from the sea floor. Some of this material is released on the way down, fueling arc volcanoes at the surface, but much of it keeps traveling into the deep Earth. This means the slab graveyard could be a massive storage vault, hiding away oceans of water and mountains of carbon far beneath the surface. Over millions of years, some of this material may leak back upward, completing a cycle that connects the deep Earth to the air we breathe. The slab graveyard may also help explain why Earth is different from other hard worlds. Plate tectonics is not present on Mars or the Moon, so there is no active sinking and no way for rock to be recycled. Since there are no pieces falling into their mantles, these bodies have been geologically dead for a long time. They have cooled and stiffened up. On the other hand, Earth's slab graveyard shows that our planet has been reusing itself for billions of years, which keeps it alive and able to support life. New tests show that the slab graveyard may hide even more secrets. Some scientists think that old slabs could stay at the boundary between the core and the mantle for more than 1 billion years. If so, they may hold records of Earth's first crust that have been washed away from the surface over time. Researchers who look at seismic signals think they may have found slabs from supercontinents that lived more than 700 million years ago. The slab graveyard is more than just a place to rest. It's also a time capsule that holds the memories of Earth's past worlds. The D double prime layer. One of the weirdest and least known layers on Earth is the D double prime layer, which is at the very bottom of the mantle and just above the outer core. They are often written as D. Even though it's only a few hundred miles thick, it might be the key to some of Earth's biggest riddles. D was found through strange earthquake activity. It's like a very thin, unstable line where the hot mantle, sinking slabs, and the fiery outer core all meet. If you think of the mantle as Earth's engine, then D is the crazy, shaking area where the gears work the hardest. The D layer sits about 1,800 miles down at the boundary where the rocky mantle meets the liquid outer core. This boundary is one of the most extreme environments on Earth. Temperatures approach 6,000 degrees Celsius, similar to the surface of the Sun, and pressures are millions of times greater than at the surface. Under these conditions, rocks behave in strange ways that we still struggle to fully understand. Seismic studies show that D is highly irregular. In some places, seismic waves shoot through it quickly, as if the rock is unusually stiff. In others, the waves crawl, suggesting patches of molten or chemically different material. Unlike the layers above, which are relatively consistent, D is chaotic, more like a patchwork quilt stitched together from different histories of Earth's interior. Subducted slabs are big plates that sink into the mantle. One main thought is that D is where these slabs finally stop. These cold, thick slabs may pile up at the base of the mantle after falling thousands of miles, making rocky mountains where the core meets the mantle. In some places of D, seismic waves may move faster because they bounce off of thick layers of old rock. In some places, the slabs may melt or react chemically with the mantle around them, creating pockets of partly liquid rock that make seismic waves move more slowly. The link between D and mantle plumes is another puzzle. Large amounts of hot rock come to the surface from the deep mantle. They feed volcanic hotspots like Hawaii and Iceland. A lot of experts think that plumes start at the base of the mantle, either inside or just above D. This idea says that D is like a plume nursery, where heat from the outer core builds up until it bursts out in a huge stream of rock. This could be why some plumes are bigger than others, or why they only show up in some places and not others. D is a jumbled and patchy structure. Recent experiments in high-pressure labs have revealed another possibility. D may contain a strange mineral called post-perovskite. Under the crushing pressures near the core, ordinary mantle minerals like bridgmanite may transform into this new phase. Post-perovskite has very different properties. It can conduct heat more efficiently and may explain some of the unusual seismic behaviors observed in D. If post-perovskite really dominates this layer, it could change how we understand heat flow from the core, the driving of mantle plumes, and even the stability of Earth's magnetic field. Since we're talking about the heart, D lies right on top of it and keeps it warm. The outer core convects based on how heat moves through D. This in turn powers Earth's magnetic field. If some parts of D are better at moving heat than others, then the outer core may be churning faster in some places and slower in others. This might be the reason why Earth's magnetic field isn't always strong, as seen in the South Atlantic anomaly today. Also, there is proof that D is not flat. According to seismic scans, it has huge mountains and valleys that are up to several miles high. These traits are not found anywhere else in the deep center of Earth. They may have formed when old slabs hit the core. Mountains on the surface are made when crustal plates crash into each other. Deep mountains in D may be made when the pieces of old ocean bottoms pile up against the core. The outer core, a sea of liquid metal. The outer core is one of the most remarkable layers of Earth. It is located about 1,800 miles below the mantle. The outer core is a huge ocean of liquid metal, mostly iron mixed with nickel and lighter elements. This is different from the solid mantle above it and the solid inner core below it. It is more than 1,400 miles thick and is always moving, boiling and churning like a pot the size of a planet. Not only is this moving sea of liquid metal interesting to look at, but it also powers the Earth's magnetic field and helps keep all living things on the surface safe. The discovery of the outer core as a liquid layer came through seismic studies. When earthquakes send shockwaves through the Earth, certain waves can't pass through liquids. Scientists noticed that some seismic waves disappeared or slowed when they reached a depth around 1,800 miles. This shadow zone revealed that the core was not entirely solid. Later calculations confirmed that the outer part of the core must be liquid, while the inner part was solid iron. This breakthrough, made in the early 20th century, completely reshaped our understanding of Earth's interior. The conditions in the outer core are extreme beyond imagination. Temperatures range from 4,000 to over 6,000 degrees Celsius, rivaling the surface of the Sun. Pressure is millions of times higher than at sea level. Under these conditions, iron and nickel, which would be solid on the surface, remain molten, flowing freely in vast currents. This is why scientists describe the outer core as a sea of liquid metal. It is the largest fluid body on the planet, larger than all the oceans combined, though of course no human will ever see it. The upper core helps make Earth's magnetic field, which is one of its most important jobs. Electric currents are made when the liquid iron and nickel spin. These currents, along with Earth's spin, create a dynamo effect on a global scale, which is a lot like a big electric generator. The magnetosphere protects Earth from solar winds and cosmic radiation. It is made up of this magnetic field that goes out into space. The atmosphere would have been stripped away a long time ago without this unseen shield. Earth would now be as empty as Mars. The flow of the outer core is not random. Seismic studies and computer simulations suggest that its liquid metal moves in giant convection currents. Heat escapes from the inner core and drives hot material upward while cooler, denser material sinks downward. These flows twist and spiral because of Earth's rotation, creating complex patterns that shift over time. Some regions of the outer core churn more vigorously than others, giving rise to magnetic hotspots and even localized weak zones in the field. The outer core doesn't just affect Earth's magnetism, it may also shape the behavior of the mantle above it. Where heat leaks out more efficiently from the core, mantle plumes may rise, leading to volcanic hotspots on the surface. This suggests that the molten outer core, though hidden thousands of miles beneath our feet, has a direct influence on where volcanoes erupt and continents shift. The fact that the upper core is always changing makes it even more compelling. The upper core of Earth powers the magnetic field, which is always changing. They move around, sometimes by tens of miles every year. The field sometimes gets weaker and even flips, with the north and south poles switching places. About 780,000 years ago, there was the last full turnaround. The outer core is the main cause of these changes. Its spinning currents slowly rearrange themselves, which makes the magnetic field above wobble, weaken, and sometimes break before it starts to form again. Some seismic evidence even hints at stratification within the outer core, with a top layer that is slightly different from the deeper liquid below. This could be a result of chemical reactions with the mantle above or from the gradual freezing of the inner core below. If so, The outer core may not be a simple, uniform ocean of molten iron, but a layered, chemically dynamic region that evolves over time. The dynamo effect. If the outer core is a moving sea of molten iron and nickel, then the dynamo effect is the machine that it drives, which is a generator on a global scale that makes Earth's magnetic field. Tens of thousands of miles into space, this field keeps charged particles from the Sun from hitting Earth and keeps the atmosphere from being pulled away. The surface of our world would have been hit by dangerous cosmic radiation without it. The oceans might not have existed, and life as we know it might not have started. But how does this engine in deep Earth really work? The answer is in the strange mix of heat, spinning, and moving liquid metal far below our feet. The core's dynamo is powered by convection. Heat from the inner core combined with radioactive decay and leftover energy from Earth's formation drives hot, buoyant fluid upward. Cooler, denser fluid sinks downward. This cycle of rising and falling molten iron forms giant currents inside the outer core, much like the rolling boil of water in a pot. But unlike boiling water, the outer core's pot is subject to intense planetary rotation, which twists these currents into spirals because of the Coriolis effect, the same force that shapes hurricanes on the surface. As these molten streams of iron and nickel move, they carry electrical charges. Moving charges create magnetic fields, and when the flows are strong and sustained, they amplify those fields in a feedback loop. The magnetic field strengthens, which in turn influences how the fluid moves, locking the system into a self-sustaining cycle. This is the essence of the dynamo effect, a churning, electrically charged engine that has kept Earth's magnetic shield alive for billions of years. How unstable the generator can be is one of the things that makes it appealing. It doesn't make a completely steady field, it wobbles, moves, and even flips. When the generator reorganizes itself, the north and south poles switch places. This is called a magnetic reversal. The field can get a lot weaker before it rebuilds in a different direction. The last time this happened was 780,000 years ago, but rocks show that it happens all the time, sometimes only tens of thousands of years apart. These flips aren't dangerous to life, but they show how random the engine is. The dynamo is also responsible for short-term changes in the magnetic field we observe today. For example, the magnetic North Pole is racing across the Arctic at nearly 40 miles per year. Regions like the South Atlantic anomaly, where the magnetic field is unusually weak, are likely caused by unusual flows in the outer core disrupting the larger pattern. These quirks suggest that the dynamo beneath us is constantly shifting, reshaping the invisible shield we depend on. New study has found some interesting information about how the inner and outer cores work together to do this. As the inner core slowly turns into crystals, it sends heat and lighter elements to the outer core. This makes it float higher, which stirs up convection even more. Another way to say this is that the growth of the inner core fuels the generator, which keeps it going. The connection between these two bodies may even be the reason why Earth's dynamo has been around longer than Mars. Since Mars's core is smaller and doesn't hold as much heat, it lost its magnetic field billions of years ago, letting the solar wind hit its surface. Experiments in laboratories have also begun to simulate the dynamo on a small scale. Using spinning spheres filled with molten sodium or liquid metals, scientists can mimic the motions of the outer core. These models produce magnetic fields similar to Earth's, proving that the principles of the dynamo effect are sound. Of course, the real outer core is vastly larger and more complex. But these experiments provide valuable clues about how fluid flows and magnetism interact in extreme environments. The inner core, Earth's iron heart. The inner core is a solid sphere of iron and nickel that is about 1,500 miles across and lies almost 4,000 miles below our feet. It is at the very center of our planet. It is about 70% the size of the Moon, and even though people will never be able to see it directly, it is very important to Earth's survival. It beats at the center of Earth and shapes the world above in ways we are only starting to understand. Scientists call it Earth's iron heart. The inner core exists under conditions so extreme that ordinary imagination falters. Temperatures are estimated to reach more than 5,000 degrees Celsius, close to the surface temperature of the Sun. The pressure is millions of times greater than what we feel at sea level. Under these crushing conditions, iron and nickel, which are molten in the outer core, are forced into a solid crystalline form at the very center. This paradox, where heat is high enough to melt metal but pressure is great enough to freeze it, creates the solid sphere we call the inner core. We know it exists because of seismic waves. When powerful earthquakes send vibrations rippling through the planet, certain waves speed up or slow down, depending on the materials they pass through. Careful studies show that some waves travel faster in the center of the Earth, indicating the presence of a dense, solid body. This was first confirmed in 1936 by Danish seismologist Inge Lehmann, whose discovery of the inner core was one of the great milestones in Earth science. Far from being a static lump of iron, the inner core is growing, changing, and possibly even spinning at a slightly different speed than the rest of the planet. As the Earth slowly cools, iron in the outer core crystallizes and freezes onto the inner core, making it expand over time. Scientists estimate the inner core grows by about 1 millimeter every year. While that may seem small, over billions of years it adds up, meaning the inner core is a relatively young feature in Earth's history. Some studies suggest it may have solidified only 1 billion years ago, long after the planet first formed. This process of change is not just noteworthy, it is necessary for life on Earth. As the inner core turns into crystals, it sends heat and lighter elements into the outer core, which is still liquid. These feed the convection currents that keep the dynamo effect going. The dynamo effect powers the magnetic field that keeps Earth's atmosphere safe. To put it another way, the inner core solidifying keeps the outer core moving, which in turn keeps our magnetic screen living. Earth's generator might have stopped working a long time ago if this process didn't happen. This would have left us open to solar winds, just like Mars. Seismic data show that it is not uniform. In some directions, seismic waves move faster, while in others, they slow down. This anisotropy suggests that iron crystals inside the core may be aligned in patterns, possibly shaped by Earth's rotation or by the inner core's slow growth. Even more intriguingly, recent studies suggest that one hemisphere of the inner core is crystallizing faster than the other, creating an asymmetry deep at the planet's center. Why this happens remains a mystery, but it could have major consequences for how the magnetic field behaves over time. More and more proof also points to the fact that the inner core may not be a single solid sphere. Some seismic studies point to an inner core, which is a smaller, clearer area in the middle that has different crystal orientations than the rest of the rock. If it's true, it means that Earth's heart is like a nested doll, with each layer having its own secret history written in iron. The line between these areas might show changes in how cool Earth is, how fast it spins, or even chemical differences that have been there since the beginning of time. The age of the inner core is another interesting question. They say it might be only 500 million to 1 billion years old, which is a lot less time than Earth has been around. If that's the case, it means that the dynamo and, by extension, the magnetic field were weaker a long time ago, which might have let more radiation reach the Earth's surface. Some people think the inner core could be up to 3 or 4 billion years old, which would mean it has been supporting the Earth for most of its past. One of the hardest things in modern geophysics is figuring out how old it really is. If we could, it would change how we think about how Earth's protective shield has changed over time. The inner core is not static either. It may actually rotate at a slightly different speed than the rest of Earth. Seismic data suggest that it sometimes spins faster or slower, in a phenomenon called super-rotation. This means Earth's iron heart might not just be growing, it is turning at its own rhythm, out of sync with the crust and mantle above. The reasons for this remain debated, but it likely reflects the push and pull between electromagnetic forces in the outer core and gravitational tugs from the mantle. The superrotation mystery. In the middle of Earth, there is a mystery called the superrotation riddle that has stumped scientists for decades. The iron and nickel-filled inner core is about 1,500 miles across and is a solid ball. It does not spin at the same speed as the mantle and crust above it. There is proof that it spins at a slightly different speed, going faster or slower at different times. The strange beat of Earth's core is like a clock with gears inside that are just out of sync with the hands you see on the outside. This idea first emerged in the 1990s, when researchers analyzing seismic waves from earthquakes noticed small but consistent differences in the time it took for waves to travel through the inner core. When scientists compared data from quakes that occurred decades apart, they found the differences matched what you'd expect if the inner core had rotated slightly faster than the rest of the planet. In other words, the core was turning ahead, like a hidden engine moving independently within Earth. The rotation rate isn't huge. Early studies suggested the inner core could be gaining about one extra rotation every few centuries compared to the surface. That might not sound like much, but for something buried 4,000 miles deep and weighing as much as the Moon, even a tiny drift is extraordinary. It means the inner core is not locked rigidly in place, but is dynamically interacting with the outer core and the mantle above it. So what causes this superrotation? The leading explanation involves the electromagnetic forces in the outer core. As molten iron flows and generates Earth's magnetic field, it exerts torque, like a twisting push, on the solid inner core. Over long periods, this push may cause the inner core to spin slightly ahead of the rest of the planet. At the same time, gravitational interactions with the mantle try to tug the inner core back into alignment. The balance between these forces could explain why the inner core's rotation isn't constant, but fluctuates. Recent investigation shows that the inner core doesn't always spin faster. According to some studies, it might slow down or even wobble, spinning a little faster than the mantle for a few decades, and then a little slower for the next few. A study from 2023 suggested that the inner core might speed up and slow down every 70 years. This cycle might even be connected to small changes in the length of Earth's days. If this is true, it means that the superrotation is not a smooth march, but a heartbeat for the deep Earth that is linked to cycles that we are just starting to notice. There are bigger problems that the superrotation puzzle raises. If it's true that the inner core turns faster than the outer core, this could change how heat and elements move between the two. The outer core powers the geodynamo, which is what makes Earth's magnetic field. The spinning of the inner core might help control how strong and stable that field is. Changes we see on the surface, like the movement of magnetic poles or a brief weakening of the magnetic field, might be linked to changes in the core's motion. The comparisons to other planets' behaviors are much more compelling. Mars used to have a magnetic field, but it lost it billions of years ago, most likely because its core cooled and its generator stopped working. One reason our generator has been going for so long might be that Earth's inner core spins very fast. It keeps the system running smoothly by adding an extra gear. This might be the reason why Earth still has a thick atmosphere and water that flows, but Mars is cold and empty. Studying the inner core's rotation is not easy. We can't send probes or cameras, so researchers rely on seismic waves from earthquakes or nuclear tests. These waves act like X-rays, passing through the core and carrying subtle clues about its structure and movement. By comparing waves from different years, scientists can detect tiny shifts that reveal how the inner core is turning. However, because the changes are so small and the data so noisy, interpretations remain hotly debated. Some scientists argue that the evidence for superrotation is strong, while others believe it could be explained by variations in the inner core's structure rather than its motion. The inner core boundary, ICB. The inner core boundary, ICB, is the outer wall of Earth's iron heart. It is a sharp line that separates the solid inner core from the moving liquid metal of the outer core. This line is about 3,200 miles below our feet. Compared to the size of Earth as a whole, it is one of the thinnest transitions, but it marks one of the most dramatic changes in state anywhere on the world. A hard, solid ball of iron and nickel is on one side. On the other side is an ocean of liquid metal that won't stop moving and stirring. These two very different worlds meet at the ICB. Seismologists first realized this boundary existed in the mid-20th century. Earthquake waves behave differently depending on whether they travel through solids or liquids. When waves hit the inner core, they speed up, showing that the material is solid. But just outside, in the outer core, they slow dramatically, proving that the metal there is liquid. The sharp contrast in wave behavior is so striking that scientists can pinpoint the ICB within just a few miles, even though it lies thousands of miles underground. The conditions at this boundary are extreme beyond human comprehension. Temperatures exceed 5,000 degrees Celsius, close to the heat of the sun's surface, yet the crushing pressure is so immense that iron solidifies despite the heat. The ICB exists because of this balance. The outer core is hot enough and under slightly less pressure to remain liquid, while just a little deeper, the higher pressures force the iron and nickel into a solid state. This thin dividing line is like a cosmic switch where liquid becomes solid in an instant. The ICB is not just a static line in Earth's interior, it is an active front of growth. As the planet slowly cools, iron from the outer core crystallizes and freezes onto the surface of the inner core. This process releases heat and lighter elements, which fuel convection in the outer core. Without this freezing at the ICB, the outer core's motions might slow, weakening or even stopping the geodynamo that generates Earth's magnetic field. In a sense, the ICB is the workshop where the inner core grows, and the dynamo above it is recharged. But the ICB is not perfectly smooth or uniform. Seismic studies suggest that in some regions, the boundary is irregular, with patches of varying thickness. In certain places, waves traveling across the ICB arrive faster or slower than expected, hinting at differences in how iron crystallizes there. Some researchers propose that the inner core may be lopsided, growing faster on one side than the other. If true, the ICB is not simply a spherical shell, but a shifting frontier shaped by uneven cooling and crystallization. There are also clues that strange chemical processes occur at the ICB. When iron solidifies, it expels lighter elements like oxygen, sulfur, or carbon into the outer core. These elements may accumulate just above the ICB, creating layers of fluid with different compositions. Such layers could affect how convection currents move, possibly explaining anomalies in Earth's magnetic field. In other words, the ICB may act as both a chemical and physical dividing line, shaping the dynamics of the entire core. The ICB is also a key part of one of the most remarkable discoveries about the deep inside of Earth: the idea of an inner core. Earth's very heart may be different from the rest of its inner core because the crystals there may be arranged in a different way. If that's the case, the ICB may not only tell the difference between solids and liquids, but it may also record different stages in Earth's temperature past, showing how the planet has changed and cooled over billions of years. Scientists can't study the ICB directly, but they can make it feel like it does in the lab. They use diamond anvil presses and huge lasers to heat and press down on very small pieces of iron and nickel to pressures of millions of atmospheres. Based on these tests, it looks like the iron crystals at the ICB might have strange shapes, like hexagonal or cubical ones, based on the temperature and pressure. The fact that earthquake waves move at different speeds and in different directions through the inner core might be due to these kinds of crystal structures. Strange anisotropy. Strange anisotropy in the inner core is one of the most puzzling things about Earth. It is more than 3,000 miles below our feet. Seismic waves, which are movements caused by earthquakes, don't always move in the same direction because of anisotropy. Moving faster going north to south through the core than going east to west is what they do. Geophysicists were shocked when they found this strange behavior in the 1980s. Why would Earth's iron heart carry waves in different ways, based on which way they are going? What does that tell us about how the planet works on the inside? The most widely accepted explanation is that iron crystals inside the inner core are not arranged randomly. Instead, they are aligned in a preferred orientation, like grains of wood in a plank. If the crystals are stacked along Earth's rotational axis, then seismic waves traveling parallel to that axis, north to south, would pass more easily, moving faster. Waves crossing the crystals at an angle, such as east to west, would encounter more resistance, slowing them down. This crystal alignment is thought to be linked to Earth's rotation, which influences how the core grows and solidifies. In recent decades, studies have shown that anisotropy in the inner core is not uniform. Some regions show stronger effects than others, and in certain areas, waves even seem to travel faster east-west rather than north-south. This suggests that the inner core is not a neat, consistent crystal ball, but a patchwork of regions with different structures. Scientists now suspect that the anisotropy reflects variations in how the inner core grows. Uneven crystallization, irregular heat flow, or even chemical differences across hemispheres. Some surprising discovery is that the inner core's eastern half seems to have stronger and sharper anisotropy than its western half. This backs up the idea that crystals are forming faster on one side of the inner core than the other, leaving behind clear patterns. Anisotropy may be the earthquake sign of an uneven core if what you say is true. One side of the Earth's heart is hardening faster than the other, making it look like the heart is beating strangely. Anisotropy may also vary with depth. Some studies suggest that the outermost layers of the inner core, just below the boundary with the liquid outer core, have weaker anisotropy than the deeper layers. This could mean that the earliest parts of the core to crystallize billions of years ago have a different texture from the layers forming today. If so, seismic waves are not only telling us about the present-day core, but also about its deep history, like tree rings revealing the growth of a forest giant. Seismic waves sometimes show evidence of small-scale anisotropy, not large hemispheric patterns, but localized regions where wave speeds deviate sharply. These patches may be caused by turbulence in the liquid outer core, disturbing crystallization at the boundary. In this sense, anisotropy could be a record of interactions between the inner and outer cores, a frozen memory of the chaotic motions above. Experiments under core-like conditions have given clues to what's happening. Using diamond anvil presses and lasers, scientists can subject iron samples to the same pressures and temperatures as the core. These experiments show that iron crystals at such extremes can take unusual forms, such as hexagonal, close-packed HCP structures. These crystals naturally align under stress, which could explain why seismic waves behave differently in different directions. But whether this lab behavior perfectly matches Earth's core remains uncertain. Some computer models show that if the inner core spins a little faster or slower than the mantle, this is called superrotation, and it can change how crystals line up, making anisotropy stronger in some places and weaker in others. This makes me think that anisotropy might not be a fixed feature of the inner core, but something that changes with the speed at which the planet spins. If scientists can decode the patterns, they may uncover the timeline of inner core formation. Was the inner core born relatively recently, about 1 billion years ago, or much earlier, almost 4 billion years ago? The way crystals are aligned could hold the answer. In fact, some researchers think anisotropy is the single most important clue we have about when and how Earth's solid core first appeared. The Earth's magnetic field is also affected by anisotropy. The geodynamo is powered by airflow in the outer core, which is changed by the growth and hardening of the inner core. If crystallization isn't even, it could change how strong and stable the magnetic field is, and it might even play a part in things like magnetic reversals. This means that strange anisotropy might have something to do with the flickering, changing shield that keeps Earth livable. The hemispheric puzzle. Scientists don't find a perfectly flat sphere when they use seismic waves to look into Earth's core. Instead, they see something strange. It looks like one half of the inner core is crystallizing faster than the other. The hemispheric puzzle is the name for this strange mismatch. It is the uneven growth of Earth's iron heart that makes us wonder more than it answers. The evidence first appeared when researchers noticed seismic waves traveled differently through the eastern hemisphere of the inner core than through the western hemisphere. In the east, beneath Asia, seismic waves moved faster and more smoothly, as though passing through well-ordered crystals. In the west, beneath the Americas, waves seemed slower and more scattered, as if traveling through a more irregular, less developed structure. This wasn't just a small anomaly. It was a global pattern, splitting Earth's deepest interior into two distinct halves. The easiest way to explain it is that the inner core is crystallizing in an uneven way. Iron from the Earth's liquid outer core freezes onto the inner core as it cools. Some people still don't agree on why this freezing seems to happen faster on one side than the other. If this is true, it means that the inner core is not a perfectly uniform sphere. Instead, it is growing unevenly, with more structure being built on one side. This could have changed the very texture of the deep core over millions of years. What could cause this imbalance? One possibility is that the mantle above is influencing how the inner core grows. The mantle is not uniform. It has hotter regions and colder regions, driven by convection currents and subducting tectonic plates. If the mantle above one side of the core is colder, it could draw heat away faster, encouraging iron to solidify more quickly there. Meanwhile, the opposite side, beneath a hotter mantle, might stay molten longer, slowing crystallization. In this way, the surface world of shifting continents and sinking slabs could indirectly sculpt the very heart of Earth. The uneven growth may also have something to do with the geodynamo, which is the spinning of liquid metal in the Earth's center that makes the magnetic field. If flows in the outer core are larger or more organized in one hemisphere, they could change how heat and matter move across the border of the inner core, which could cause crystallization to happen unevenly. The hemispheric puzzle could be thought of as a feedback loop in this way. The uneven growth of the inner core changes the flows in the outer core, which in turn makes the uneven growth worse. Uneven growth would produce mechanical stress inside the core, since one side is pushing outward more than the other. Over geological timescales, this could affect the alignment of iron crystals, contributing to anisotropy, the directional differences in seismic wave speeds we see today. It might also explain why Earth's magnetic field has shifted, weakened, and even reversed so many times throughout history. A lopsided inner core could inject irregularities into the outer core's convection, disrupting the dynamo engine that powers our shield. Some researchers propose that this uneven growth may have created a kind of inner drift. As iron crystallizes more on one side, the entire inner core might slowly shift eastward within the liquid outer core, almost like a ball settling in a tilted bowl. If true, then Earth's inner core is not perfectly centered. It is slightly offset, pulled by billions of years of uneven growth. Some seismic readings show that the difference between the hemispheres is not just in growth rates, but also in the way the crystals are arranged. In one half of the Earth, the iron grains seem to be lined up in a way that makes it easy for earthquake waves to travel from north to south. The crystals are mixed in the other one, which slows down the waves. It looks like the hemispheric puzzle isn't just about crystals going faster or slower. It's also about very different processes going on in each half of the core. How old the inner core is also linked to the geographic puzzle. It's possible that the inner core as a whole formed not long ago, maybe even just 1 billion years ago, if one side is younger and crystallizing more quickly. At that time, there is proof in Earth's natural record of a magnetic field getting stronger. In this case, the inner core's uneven growth might not just be interesting. It might be the reason Earth's dynamo has been going for so long. This puzzle highlights how interconnected Earth truly is. The continents drifting on the surface, the slabs sinking into the mantle, the flows in the outer core, and the growth of the inner core are all part of the same system. What happens thousands of miles down may leave a fingerprint on the surface, in the movement of magnetic poles or in the history of geological time preserved in rocks. The core's hidden heat. For most people, the Earth's core looks like a big ball of hot metal that glows like a kiln. That picture isn't completely wrong, but scientists have been wondering for a long time what keeps the core so hot. The sun gives us most of our energy from the outside, but deep inside the Earth, there's another engine. The geodynamo, which makes the Earth's magnetic field, is powered by this secret heat. It also keeps the core liquid. It keeps Earth from getting too hot from the sun. Without it, Earth would just be a cold, quiet rock. For a long time, scientists thought the heat inside Earth came mainly from two sources: leftover energy from when the planet first formed, and the slow cooling of the core as iron solidifies onto the inner core. But newer research shows there may be another, equally important heat source: radioactive decay. Tiny amounts of radioactive elements buried deep in the planet act like miniature furnaces, releasing heat as they break down. This discovery has reshaped how we think about Earth's deep interior. The main suspects are elements like potassium-40, thorium-232, and uranium-238. These isotopes release energy when their atoms decay, and while they're rare compared to iron or nickel, even small amounts add up over billions of years. On the surface, we can detect their heat in the crust through volcanic activity and geothermal energy. But in the core, their presence is much harder to prove. Scientists can't drill anywhere near that deep, so they rely on indirect clues. Helium atoms give us one of the most exciting hints. Volcanic plumes that come up from deep inside Earth can carry helium-3, a rare form of helium that is thought to be primordial and from the time when Earth was first formed. Other helium atoms, like helium-4, can be made by radioactive breakdown, though. By measuring the amounts of these gases, we can get a sense of the presence of radioactive elements deep below. Some volcanic hotspots, like those in Hawaii and Iceland, have strange isotope ratios that point to a link to reserves deep inside the Earth. Geoneutrinos, which look like ghostly particles and are made when nuclear materials break down, are another hint. These particles go right through Earth, and huge devices buried deep underground can pick them up. Geoneutrinos are mostly from the crust and mantle, but their signals may also have signs of nuclear decay in the core. New tests are just beginning to scratch the surface, but they show that radioactive heating in the deep core is more important than was thought before. If radioactive elements are indeed present in the core, they could explain a long-standing mystery: why Earth's core is still molten today. Simple cooling models predict that the core should have solidified much more by now. But the presence of radioactive decay provides a steady, long-term heat source that prevents the core from freezing entirely. This extra heat also keeps convection in the outer core vigorous, ensuring that the geodynamo continues to generate our protective magnetic field. The hidden heat may also explain variations in the core's behavior. For instance, the growth of the inner core appears uneven, with one hemisphere crystallizing faster than the other. If radioactive elements are unevenly distributed, some regions of the core could release more heat, slowing crystallization there, while cooler regions solidify more quickly. This could connect radioactive decay directly to the hemispheric puzzle seen in seismic studies. How did the toxic stuff get into the core in the first place? This question leads to a lot of discussion. Most radioactive isotopes are lithophile, which means they'd rather stay in the hard basement than mix with iron. But because Earth was so hot and under so much pressure in the past, some of these isotopes may have sunk into the core during planetary division. On the other hand, radioactive elements might be found in very small amounts, stuck in iron alloys, or mixed with light elements like carbon or sulfur. That much would be enough to keep the core warm for billions of years if even a small amount got there. The hidden heat also raises questions about Earth's long-term future. As radioactive isotopes decay, their energy output decreases. Uranium and thorium have half-lives of billions of years, meaning they'll continue to provide warmth far into the future. But eventually, the supply will dwindle. When that happens, the core will cool more quickly, the inner core will expand, and the outer core may eventually freeze solid. Without a liquid outer core, the geodynamo will stop, Earth's magnetic field will collapse, and our planet will lose its shield against solar winds. This is exactly what seems to have happened on Mars. Its smaller size meant it cooled faster, its core solidified, and its magnetic field died billions of years ago. The light element mystery. The Earth's core looks like it should be easy at first glance. Earth's core is mostly made up of iron and nickel, which are the two largest metals and sank to the center when the planet formed. But when experts figure out how dense the core is, they find that it's not iron-nickel at all. I think there are lighter parts in there that make the body less dense than thought. This puzzle is called the light element mystery, and figuring it out could help us understand how Earth formed, its deep chemistry, and even why it is so different from nearby planets like Mars and Venus. The evidence comes from precise seismic and laboratory studies. Seismic waves passing through the core travel slower than they would through pure iron-nickel, suggesting another ingredient is present. Computer models also show that the outer core is about 10% less dense than pure iron. That gap may sound small, but at planetary scale, it means hundreds of millions of tons of lighter material must be hiding inside. What are these light elements? Scientists have a short list of suspects: sulfur, carbon, silicon, oxygen, and hydrogen. Each of these elements behaves differently under core-like pressures, and each could leave unique fingerprints on Earth's magnetic field, inner core growth, and seismic behavior. The difficulty is that no one knows exactly which elements, or in what proportions, are mixed into the iron ocean. Sulfur is a strong candidate. It bonds easily with iron and was abundant in the solar nebula from which Earth formed. If significant amounts of sulfur sank into the core, it could explain some of the density deficit. However, sulfur-rich cores are predicted to solidify differently than what we see today, so sulfur alone may not be the full answer. Oxygen is another possibility. During Earth's violent beginnings, collisions with other planetesimals may have injected oxygen into the core. Experiments show that oxygen can dissolve in molten iron under extreme pressure. If oxygen is present, it would make the outer core less dense, and could also help explain why parts of the mantle show signs of ancient oxygen-rich material rising from below. Carbon is particularly intriguing. If dissolved in iron, it could explain the lighter density of both the outer and inner cores. Some geologists think the core may hold as much carbon as the entire surface world, locked deep inside in metallic alloys. If true, the inner Earth may be the planet's largest hidden carbon reservoir, playing a silent but critical role in Earth's carbon cycle over billions of years. Silicon is also a prime suspect. Computer simulations show that silicon mixes well with iron under extreme pressure and could account for a significant portion of the density gap. If silicon dominates, it may mean Earth formed under more reducing oxygen-poor conditions than we thought, changing our view of how the early solar system shaped our planet. Hydrogen, though tiny, cannot be ruled out. Some scientists propose that water delivered by asteroids or comets in Earth's youth may have broken apart, sending hydrogen into the core. If hydrogen is indeed present, it would be locked at unimaginable pressures, possibly forming exotic compounds never seen at the surface. Not only is the light element riddle interesting for chemists, but it also has an effect on how the core works now. For instance, as iron freezes on top of the inner core, lighter elements in the outer core are pushed out. This pushing out makes the outer core float higher, which improves circulation and helps the geodynamo work. convection might not work as well without those light elements, and Earth's magnetic screen might not be as stable. In this way, the fact that Earth has light elements may be one of the main reasons why it has been livable for so long. Recent breakthroughs have provided fresh clues. High-energy experiments using diamond anvil cells and powerful lasers have recreated core pressures and shown that mixtures of iron with silicon, carbon, or oxygen could indeed match seismic observations. Some studies suggest the outer core may contain a blend of silicon and oxygen, while the inner core may favor carbon or hydrogen. This hints that the core's composition is layered, with different light elements concentrated at different depths. Seismology has also helped solve the puzzle. If the inner center were made of pure iron, waves passing through it would act in a certain way. Instead, their speeds point to the presence of small but significant amounts of light elements that are messing up the structure of the crystal. This helps explain anisotropy, which means that wave speeds vary depending on the way they are traveling. The secret of the light factor is even linked to the story of how Earth came to be. What kind of light elements are in the core that can tell us about the conditions when Earth was being formed? For instance, a core high in silicon would suggest that Earth formed in a part of the solar nebula that didn't have much oxygen. A core high in oxygen, on the other hand, would mean that Earth gathered matter from a zone with more oxygen. This way, Earth's secret heart might still have a chemical record of how it was violently formed 4.5 billion years ago. The core-mantle boundary mountains. We wouldn't be able to find a smooth line between rock and metal at the bottom of Earth's core, which is about 1,800 miles below the surface. It turns out that seismic imaging has shown something much stranger. Mountains bigger than Everest are right at the edge of the core. These huge buildings, which are buried in darkness forever, are one of the least known things about Earth. They are called core-mantle boundary mountains by scientists, and their discovery is changing the way we think about how the Earth was formed. The evidence comes from seismic waves. When earthquakes strike, their vibrations race through Earth and sometimes bounce off the mantle core boundary. If this boundary were perfectly smooth, those waves would scatter in predictable ways. But instead, seismologists noticed irregularities, delays, echoes, and distortions that pointed to rough topography. By carefully analyzing these signals, they concluded that vast mountain ranges exist just above the liquid outer core. Some of these hidden peaks may rise tens of miles high, dwarfing anything on the surface. What are these buried mountains made of? The leading idea is that they are piles of ancient, dense rock pushed downward by plate tectonics. Over billions of years, tectonic slabs from the surface have sunk into the mantle, carrying chemically distinct material deep into the planet. At the mantle's base, this material may accumulate, forming ridges, plateaus, and towering structures at the core-mantle boundary. In this sense, the mountains beneath us could be graveyards of continents, built from the remains of long-lost oceans and crustal plates. There is another option, though. The mountains could be places where the mantle and core interact chemically. At the border, there are huge differences between the solid rock above and the liquid metal below. In some places, iron may seep into the mantle from the surface, changing its makeup and mass. In some, lighter elements from the surface may sink to the bottom and build up into thick layers. These processes could create highs and lows in the land, shaping the rough, rocky environment that scientists see today. On Earth's surface, mountain ranges like the Himalayas are dramatic, but they are mere wrinkles compared to what lies deep inside. Seismic data suggests some of these structures are 5 times taller than Mount Everest and span thousands of miles. If we could strip away the planet's layers and look at the core-mantle boundary directly, we would see a jagged alien terrain stretching across the entire globe. What role do these mountains play in Earth's systems? One key idea is that they act as anchors for mantle plumes. Mantle plumes are hot upwellings that rise from deep inside Earth and create volcanic hotspots like Hawaii and Iceland. The mountainous terrain at the core-mantle boundary may help channel and focus these plumes, guiding them upward through the mantle until they erupt at the surface. In this way, the invisible mountains may be linked to some of Earth's most dramatic volcanic events. They may also influence plate tectonics itself. The mountains create uneven boundaries where heat and material flow differently. These differences may affect convection in the mantle, the process that drives plate motion on the surface. In other words, the continents moving above our heads might be responding to the shape of a hidden mountain range nearly 2,000 miles below. New research using better seismic tomography, which is like an X-ray of the Earth in 3D, has shown that these mountains are not spread out evenly. Some places, especially those under the Pacific Ocean, look like they have very rough terrain, while others look like they have mostly smooth terrain. This shows that the border isn't smooth and is shaped by local processes such as subduction and plume formation. It's also not clear if these mountains are fixed or moving. Are they fixed in place, having been built billions of years ago and not changed? Or do they keep moving, breaking apart, and putting themselves back together as new slabs of crust fall? Some experts believe the second option is more likely, and that these mountains are an important part of Earth's deep recycling system, changing all the time as the surface changes. Certain hotspots produce lava with unusual isotopes, hinting that their material may have been stored near the core-mantle boundary for billions of years. If so, then these mountains are not just inert piles of rock, they are reservoirs of ancient Earth material, preserving a record of the planet's earliest history. Ultra-low velocity zones, ULVs. Scientists have found strange spots where earthquake waves suddenly slow down to a crawl at the very bottom of Earth's mantle, just above the hot outer core. Ultra-low velocity zones, or ULVZs, are some of the most mysterious places in the deep core of Earth. Being only a few tens of miles thick, they show that something very strange is happening right at the boundary between the core and the mantle. The name comes from their effect on seismic waves. When earthquakes send vibrations through Earth, waves usually speed up or slow down in predictable ways, depending on the material they pass through. But when these waves hit ULVZs, their speeds drop by as much as 30%. That's a huge anomaly in seismic terms, like suddenly hitting a pocket of sludge inside otherwise solid rock. So, what are ULVZs made of? One leading theory is that they are regions of partially melted rock, leftovers from the very beginning of Earth's history. When the young planet was still forming, its outer layers were likely covered in a global magma ocean. Over time, most of that magma cooled and hardened into the solid mantle we know today. But some fragments may have sunk to the bottom, trapped near the core. Billions of years later, they still survive as thin, ultra-dense patches, fossils of Earth's fiery birth. A different theory is that ULVZs might have more iron than usual. Iron-rich rocks become very dense and slow down seismic waves when they are exposed to the high temperatures at the base of the mantle. If ULVZs have a lot of iron, it means that the core and mantle may be chemically reacting with each other and trading material in ways we don't fully understand. In this way, ULVZs might be like the mixing zones of the deep Earth, where metal and rock come together and mix. Some experts even think that ULVZs might be the remains of a huge impact that happened a long time ago. A rock about the size of Mars, sometimes called Theia, is thought to have crashed into Earth early in its past, making the Moon. A lot of the young Earth would have melted in that disaster, and strange chemical mixes would have been spread out in the core. ULVZs could be the last places that ancient trash is hidden, as it is kept safe deep in the planet's core. Whatever their origin, ULVZs appear to play an important role in Earth's dynamics. They are often found at the base of mantle plumes, the hot upwellings that rise from deep within Earth and feed volcanic hotspots like Hawaii and Iceland. ULVZs may act as launch pads for these plumes, providing the heat or chemical spark that drives them upward. If so, the hidden structures could be directly linked to some of the most powerful volcanic eruptions in Earth's history. The size of ULVZs varies dramatically. Some are only a few dozen miles wide, while others may be hundreds of miles across. Seismic studies beneath the Pacific Ocean, for example, suggest the presence of enormous ULVZs sprawling across the mantle core boundary. These giants may underlie entire volcanic provinces, feeding activity at the surface for tens of millions of years. Studying ULVZs is difficult because they are so thin and so deep. Traditional seismic tomography, which creates blurry 3D images of Earth, often struggles to capture such fine features. Instead, scientists rely on subtle signals like wave scattering and seismic echoes, which can reveal where waves have encountered an unusually soft patch. Recent advances in global seismometer networks are helping sharpen these images, slowly turning vague blobs into clearer structures. It was surprising to learn that not all ULVZs are the same. Some of them act almost like tiny lava lakes hidden miles below, like they are partly melting. Some look solid, but they are made of different materials that can't be found anywhere else in the mantle, so their chemicals are different. This variety shows that ULVZs are not just one thing, but a group of structures, each shaped by its own natural past. Their connection to the superplumes, the giant upwellings of hot rock beneath Africa and the Pacific, is especially intriguing. ULVZs tend to cluster around the edges of these vast structures, almost like hot embers at the base of a fire. This pattern hints that ULVZs may influence where superplumes form, shaping volcanic activity on a continental scale. In this way, the tiniest deep Earth features may help steer some of the largest geological processes we see at the surface. Giant core structures. Two of the biggest secrets in the world are buried deep below our feet, just above the molten outer core of Earth. Seismic studies have shown that at the base of the mantle there are blobs of thick material the size of continents that are thousands of miles wide and hundreds of miles tall. Large low-shear velocity provinces, LSVPs, are the official name for these formations, but many scientists just call them giant core structures. They are some of the strangest things ever found inside Earth because of how big they are and where they came from. Seismic tomography, which uses earthquake waves to make maps of the inside of Earth, gave us our first clues about these structures. Scientists found that seismic waves move much more slowly through some areas of the lower core than in others. This suggests that the rock in those areas is especially dense and hot. Over time, it became clear that these slow zones weren't just random spots, but huge areas of strange matter. The other one is under the Pacific Ocean, and the first one is under Africa. They are all so big that if we could lift them to the surface, they would be about the same size as countries. What are these giant blobs made of? The leading idea is that they are composed of chemically distinct rock, denser than the surrounding mantle. Some scientists believe they are reservoirs of ancient material dating back to Earth's formation. When the young Earth experienced a global magma ocean, some parts may have crystallized differently, sinking and becoming trapped near the core. Over billions of years, these dense pockets could have persisted, forming the massive provinces we see today. In another concept, they are linked to subsidence and plate tectonics. They bring rocks, marine crust, and minerals that are high in water with them as they sink into the mantle. Over time, these things may build up at the base of the wall into thick piles. If this process went on for billions of years, it might explain why the giant core structures are so huge. The blobs might be the last pieces of Theia, the protoplanet that crashed into Earth and made the Moon. This idea says that during the impact, pieces of Theia's mantle sank deep into Earth's center and became lodged near the core. If this is true, then these huge buildings are made of alien matter that has been preserved for 4.5 billion years and is still changing Earth from the inside. Regardless of their origin, the giant core structures appear to play a crucial role in Earth's geology. They are often linked to mantle plumes, the rising columns of hot rock that create volcanic hotspots like Hawaii, Iceland, and Yellowstone. Seismic studies show that plumes often originate near the edges of these blobs, as if the blobs act as plume nurseries, guiding heat upward toward the surface. This means the blobs may indirectly control the location of some of Earth's most powerful volcanic activity. The blobs also seem to influence supercontinent cycles. Some geologists argue that the upwellings from these giant structures have helped break apart ancient supercontinents like Pangaea. Their positions may even explain why continents tend to cluster and split in repeating cycles over hundreds of millions of years. In this sense, the blobs are like hidden architects of Earth's surface geography. Volcanic rocks are another sign of how important they are. Lava from some hotspots like Hawaii and Samoa has strange chemical fingerprints. Based on these isotopic fingerprints, it looks like the magma comes from sources that have been sealed off deep in the core for billions of years. The big blobs are the most likely cause. So the blobs might be like time boxes that hold chemical data from Earth's early days, when it was still forming from the solar nebula's dust and gas. Are the blobs solid or partially molten? Are they slowly moving or anchored in place? Some models suggest they may drift over geologic time, merging or splitting like colossal lava lakes. Others propose they are relatively stable, rooted in position for billions of years. Interestingly, the blobs beneath Africa and the Pacific are not symmetrical. The African blob appears to be taller and less stable. This could explain why Africa has such intense volcanic activity and rifting compared to other regions. Some recent findings even suggest that these blobs might go up into the mantle transition zone, which is a lot higher than the limit between the core and the mantle. If what they say is true, they are not just isolated features. They are huge walls of strange rock that go deep into the Earth. Being on a par with the size of Earth's core, these buildings would be some of the biggest around. To study them more closely, scientists rely on a combination of seismic data, laboratory experiments, and computer simulations. High-pressure experiments have shown how certain minerals could match the unusual densities of the blobs. Meanwhile, advanced 3D models of mantle convection suggest that the blobs may affect the entire flow of heat inside Earth, shaping not only volcanism, but also the long-term cooling of the planet. The origin of Earth's magnetism. It is one of the most amazing shields in the solar system that Earth has. The solar wind is the sun's constant stream of charged particles. Without it, our atmosphere would be gone, our electronics would break, and the surface would be covered in radiation that is bad for living things. But this shield can't be seen and isn't steady or easy. It flickers, shakes, gets weaker, and sometimes even flips over geologic time. There is a process deep in Earth's core called the geodynamo that makes this guardian change all the time. To figure out how it works, you have to peel back layers of mystery about metal, heat, and motion 4,000 miles below. The magnetic field begins with Earth's outer core, a vast ocean of molten iron and nickel. This liquid metal conducts electricity, and as it moves, it generates currents. But motion alone isn't enough. What makes Earth unique is the combination of convection and planetary rotation. Heat from the core's interior rises upward, while cooler material sinks, setting up swirling currents. Because Earth spins, these flows twist and spiral into complex patterns. The result is a self-sustaining dynamo. Moving metal generates a magnetic field, and that field, in turn, helps organize the flows that keep it alive. The discovery of Earth's magnetic origin was gradual. For centuries, people noticed that compasses always pointed north, but the explanation remained unknown. It wasn't until the 20th century that seismology revealed Earth's layered structure, and geophysics showed that only the molten outer core could power such a strong, long-lasting field. Today, we know the field extends far into space, forming the magnetosphere, which deflects solar wind particles and channels some into spectacular auroras near the poles. The details of the dynamo remain puzzling. One key question is, what drives the convection in the core? The main source is the cooling of Earth itself. As the planet radiates heat into space, the outer core loses energy and convects. But there's a second driver, the growth of the inner core. As iron solidifies onto the inner core, lighter elements like oxygen and silicon are expelled into the outer core. This makes the surrounding fluid more buoyant, stirring it like a pot of boiling soup. Together, thermal and compositional convection keep the dynamo churning. The field's long history is another secret. Minerals from 3.5 billion years ago that still have magnetism in them show that Earth's magnetic field has been around for a very long time. That's amazing, because convection needs a very careful balance of energy to last for billions of years. The engine might have stopped working a long time ago if Earth had cooled down too quickly. A weak field might not have been able to hold it together if it cooled down too slowly. The center of Earth was just right, but Mars and the Moon lost their magnetic shields billions of years ago. Radioactive elements, such as potassium, uranium, and thorium, may provide an extra secret heat source in the core, according to new studies. If there are large amounts of these elements deep in the Earth, their slow breakdown would release energy over billions of years, which would make the engine last longer. This might help show why Earth's field has been around longer than Mars, whose core may have cooled down too quickly because it is smaller. The field's strange behavior is another problem. It usually goes from south to north, but it isn't always straight. The field drops, moves, or even flips every so often. In a reverse, south turns into north and north turns into south. Rarely, about once every few 100,000 years, these flips happen. The most recent full turnaround happened about 780,000 years ago. The dynamo's random flows seem to make these flips possible, but no one knows for sure what causes them. Modern satellites like Swarm, operated by the European Space Agency, are helping scientists track the field's variations in real time. These measurements show that the field is currently weakening, especially in a region called the South Atlantic Anomaly, where radiation from space can penetrate unusually close to Earth's surface. While this doesn't mean an imminent reversal, it does highlight how dynamic and unpredictable the dynamo can be. Earth's dynamo may not be unique in the solar system. Jupiter and Saturn also have powerful magnetic fields generated by metallic hydrogen in their deep interiors. Mercury, despite its small size, manages to sustain a weak field, while Venus, which is almost Earth's twin in size, has none. Comparing these planets helps scientists understand why Earth's dynamo has been so stable and life-sustaining, while others failed or never started. Magnetic reversals. Most of the time, every direction points north. However, Earth's magnetic field will change over time. The Earth's magnetic poles have moved around over time, with north becoming south and south becoming north. These things, known as magnetic reversals, are some of the most interesting things that Earth's unseen shield does. Their effects can be felt in the Earth's atmosphere, rocks, and even living things, even though they take thousands of years to happen. Evidence for reversals comes from an unlikely place: volcanic rocks. When lava cools, the iron-rich minerals inside align with Earth's magnetic field, locking in its direction like a natural compass. By studying ancient lava flows on different continents, scientists discovered that at certain times in the past, the magnetic field was reversed. What we call the North Pole today once pointed south, and vice versa. These magnetic fingerprints are also found on the seafloor, where new crust forms at mid-ocean ridges. Stripes of rock alternate in polarity, creating a barcode-like record of flips going back hundreds of millions of years. The last full reversal, called the Brunner-Matuyama reversal, happened about 780,000 years ago. But reversals don't follow a neat schedule. Sometimes they happen every 200,000 years. Other times, tens of millions of years pass without one. For example, during a period known as the Cretaceous normal superchron, lasting from about 120 to 83 million years ago, Earth's field stayed in the same orientation for nearly 40 million years. Then suddenly, flips returned. This irregularity shows that reversals are the product of chaotic processes deep inside the core. So what actually causes a reversal? The leading explanation points to the geodynamo in Earth's liquid outer core. The swirling motions of molten iron generate the field, but those flows are turbulent and unstable. Computer simulations show that sometimes the field weakens, breaks apart, and reconfigures in the opposite direction. Think of it like a messy whirlpool. Most of the time it spins one way, but under the right conditions, it can stall and flip to the other. Reversals don't happen right away. It takes thousands of years for them to happen. First, the field gets weaker, then it gets chaotic, and finally it starts to build back up in the opposite way. Earth's magnetic field doesn't go away completely during the shift, but it does get weaker and messier. There may be more than one magnetic pole in different parts of the world, not just one that points north to south. In those conditions, compasses would not have worked because they would have spun randomly from one way to another. One big risk about reversals is what they might do to Earth's magnetic shield. When the field gets weaker, more charged particles from the solar wind can reach the atmosphere of Earth. The magnetosphere blocks most of this radiation now, but during a reversal, more could get through. This makes it more likely that satellites, power lines, and electrical systems will be damaged. People and animals would still be safe on the ground because of the atmosphere, but auroras would probably spread out and show up even in warm clouds. Fossil records suggest that reversals haven't caused mass extinctions, which means life generally adapts. Birds, turtles, and other animals that navigate using Earth's field might struggle during the transition, but they likely use other cues, like stars or smells, to find their way. Humans, of course, didn't exist during the last reversal, but future civilizations would have to cope with the effects on modern technology. Earth's field doesn't only flip, it sometimes tries to flip, but fails. These events are called geomagnetic excursions, where the field weakens and shifts dramatically, but then snaps back to its original orientation. One famous case is the Lachon event, about 41,000 years ago. For a few centuries, the magnetic field nearly collapsed, and the poles wandered close to the equator, before returning to normal. Evidence from caves, sediments, and ice cores shows that during this time, radiation levels at the surface increased significantly, leaving detectable traces of isotopes like beryllium-10. The irregularity of reversals makes predicting the next one extremely difficult. Some scientists point to the current South Atlantic anomaly, a weak spot in the magnetic field stretching from South America to Africa, as a possible sign of an approaching reversal. Satellites passing through the anomaly often malfunction due to increased radiation. While this doesn't guarantee a flip, it suggests the field is behaving unusually, perhaps entering the early stages of long-term change. Computer models provide valuable insight. By recreating the turbulent flows of the outer core, simulations can reproduce reversals that look strikingly similar to those recorded in rocks. These models show that reversals are not catastrophic breakdowns, but natural outcomes of a restless dynamo. The key drivers are thought to be changes in heat flow at the core-mantle boundary, interactions with giant core structures, or variations in the growth of the inner core. The weakening field. The Earth's magnetic field guards us from the Sun's steady stream of charged particles. It's like an invisible guardian, but this shield can be broken. Earth's magnetic field is weakening, especially in a large area known as the South Atlantic Anomaly, SAA, according to new data. There are different opinions on whether this weakness is the start of a pole reversal or just one of the normal wobbles that the geodynamo does from time to time. The South Atlantic Anomaly stretches across South America and the southern Atlantic Ocean, reaching as far as Africa. In this region, the magnetic field is much weaker than the global average. Satellites passing overhead often experience technical glitches because radiation from space can penetrate deeper into Earth's atmosphere, where the shield is thinnest. Instruments aboard the Hubble Space Telescope, for example, are powered down when flying over the anomaly to prevent damage. It's as if Earth's armor has a soft spot, a dent in its otherwise strong shield. The anomaly is growing. Over the past 200 years, scientists have observed the magnetic field overall weaken by about 10%, but the South Atlantic anomaly has deepened and expanded more rapidly. Today, it covers an area about 5 times the size of the continental United States, and its weakest point is drifting westward at a pace of about 20 kilometers per year. This kind of change is incredibly fast on a geologic timescale. So what causes the weakening? The answer lies deep inside Earth's outer core. The magnetic field comes from swirling molten iron, but those flows are not steady or simple. They twist, wobble, and sometimes cancel each other out. In the South Atlantic region, the geodynamo seems to be producing magnetic patches that oppose the global field. When these patches rise toward the surface, they reduce the strength of the field above, creating the anomaly we detect today. For now, the field is still strong enough to protect life on Earth. The atmosphere itself acts as a second shield, blocking harmful radiation even where the magnetic field is thin. But the weakening has important implications for our technology. Satellites, GPS, power grids, and radio communications are all vulnerable to solar storms. As the field weakens, these systems become more exposed. A strong solar storm today could potentially knock out power in large regions of the world, costing trillions of dollars in damage. The weakening also affects our ability to navigate. For centuries, humans relied on compasses aligned with Earth's magnetic field. Today, even though we use satellites for positioning, compasses are still vital in aviation, military operations, and exploration. A weakening and wandering field means adjustments must constantly be made. In fact, the World Magnetic Model, which helps guide everything from airplanes to smartphone maps, had to be updated in 2019, 2 years earlier than scheduled, because the North Magnetic Pole was drifting faster than expected. Another area of concern is cosmic radiation exposure. Astronauts in low Earth orbit already face increased radiation risk, but as the field weakens, they are more exposed when passing over the South Atlantic anomaly. Airplane passengers on high-altitude polar flights may also receive slightly higher doses of radiation. While not immediately dangerous, this adds to long-term risks for frequent flyers and astronauts alike. But what the weakened field tells us about the inside of Earth might be the most fascinating information about it. The South Atlantic anomaly is thought to be connected to one of the big core features deep inside the Earth. It is located just above the border between the core and the mantle, below Africa. It's possible that this strange, thick area is stopping the flow of molten iron, which is making the magnetic field lines at the surface bend and weaken. In this way, the strange thing isn't just a quirk. It's a look into the deep workings of Earth's core. The big question is whether this weakening is temporary or the start of a full reversal. Historical data suggests the field has weakened before without flipping. During the Lachaume event, about 41,000 years ago, the field nearly collapsed but recovered. On the other hand, full reversals are part of Earth's history, and the average time between them is about 300,000 years. Since the last reversal was 780,000 years ago, we are overdue by that measure. Seismic probes of the core. We are not able to drill to the Earth's center. That being said, the Kola superdeep borehole in Russia, which was the deepest hole ever dug, only went 7.6 miles deep, which is less than 0.2% of the way to the center. El Niño and other natural disasters are the only way for experts to really see what's thousands of miles below our feet. Every time a big earthquake shakes the Earth, shockwaves rush through the core. Earth's secret layers can be pieced together by geophysicists who study how these waves move, bend, and slow down. There are two main types of seismic waves: P waves, primary waves, and S waves, secondary waves. P waves compress and expand material, like sound waves, and can travel through solids, liquids, and gases. S waves move material side to side, like shaking a rope, and can only move through solids. This simple difference has revealed one of the greatest secrets of Earth's interior. Because S waves disappear when they reach the outer core, we know the outer core must be liquid. Meanwhile, P waves slow dramatically as they enter the core, giving scientists more clues about its composition and density. When an earthquake occurs, seismometers all over the world record the arrival of these waves. By comparing their arrival times at different stations, scientists can map how the waves traveled through Earth. Over decades, as seismometer networks expanded, researchers began to notice strange patterns. For example, certain parts of the core cause waves to bend more than expected. Others slow them down. These variations tell us that the core is not uniform, but filled with complexity. One breakthrough came in 1936, when Danish seismologist Inge Lehmann discovered the inner core. By carefully analyzing faint seismic signals, she realized that some P waves were bouncing off a boundary deep within Earth. This was the first evidence that the core was not entirely liquid, but contained a solid center. Her discovery completely reshaped our understanding of Earth's structure and remains one of the most important findings in geophysics. Modern seismic studies have gone far beyond that first discovery. Today, researchers use thousands of earthquake recordings, combining them into detailed 3D maps of Earth's interior. These seismic tomographic maps are like CT scans of the planet. They reveal not just the liquid outer core and solid inner core, but also strange anomalies such as ultra-low velocity zones and giant core structures. Without seismic data, these features would be invisible. The study of seismic variation in the deep core is a useful use. Scientists found that P waves move a little faster from north to south than from east to west. This makes me think that the iron crystals in the inner core may be lined up in a certain way, which could be caused by how the core grows and crystallizes. Seismic probes are the only ones that can find such tiny things. The idea of an inner core is another amazing finding. Seismic waves point to a smaller, clearer area inside the core where the crystal structure might be different from that on the outside. This could mean that the Earth's core has changed over time, with records of different stages of growth deep inside. This level of detail is only possible because earthquake waves can go through layers that we can't reach with our hands. The accuracy of seismic probing has improved dramatically thanks to global earthquake monitoring. The global seismographic network and regional arrays provide high-resolution data, allowing scientists to detect even small differences in wave speeds. These differences reveal changes in composition, temperature, and phase deep below. For instance, experiments show that iron at core pressures behaves differently depending on whether it is solid or liquid. Comparing lab results to seismic data helps refine models of the core's makeup. Seismic probes also uncover mysteries. Some waves that pass through the core show tiny delays or unexpected bending, suggesting hidden complexities. One hypothesis is that the outer core is not a simple iron-nickel mix, but contains lighter elements like oxygen, sulfur, or silicon. These impurities may change how waves travel, and seismic data provides the best evidence of their presence. Another idea is that the boundary between the inner and outer core isn't perfectly smooth, but has irregularities, like mountains on Earth's surface, except thousands of miles below. Even artificial seismic waves have been used to probe the core. Large explosions, like nuclear tests during the Cold War, sent shockwaves through Earth that scientists secretly measured to gain information about the interior. Today, with international bans on such tests, researchers rely on natural earthquakes and sophisticated computer models. Seismic probing has even helped confirm that the inner core may be rotating at a different speed from the rest of the planet. Subtle changes in how waves pass through Earth over decades suggest the inner core spins slightly faster than the mantle and crust. This superrotation is still debated, but seismic evidence is our best window into testing such theories. Shockwave experiments. Scientists have used a different type of experiment to simulate the crushing pressures and burning heat that are found 4,000 miles below the surface of the Earth. These are some of the most extreme tests that have ever been made in a lab. They are called shockwave studies. Scientists can quickly recreate the conditions that exist inside Earth's core by hitting metals with huge lasers or powerful explosives. The results tell us very little about what the core is made of, how hot it might be, and how it reacts to stress that we can't even imagine. The principle behind shockwave experiments is simple. When a sudden force strikes a material, it sends a wave of compression racing through it. That wave raises the material's pressure and temperature to levels far beyond what normal laboratory tools can achieve. By carefully measuring how the material responds, scientists can mimic the physics of the deep Earth. It's like a miniature earthquake in a metal sample, except controlled and precisely measured. With the most powerful laser in the world, the National Ignition Facility, NIF, in California, is one of the most well-known places where these tests are done. Scientists at NIF point 192 lines of laser light at a very small object, giving it more than 1 million joules of energy right away. This energy makes a shock wave that squeezes the sample to pressures higher than 3 million times Earth's atmosphere, which are about the same as the pressures at the boundary between Earth's outer core and inner core. Even though the material only lasts billionths of a second, that time is long enough to see how sound waves move through it, how thick it gets, and whether it stays rigid or melts. These experiments have already delivered some surprising results. For decades, estimates of the core's temperature varied widely, from 4,000 degrees Celsius to as high as 7,000. Shockwave tests on iron under core-like pressures suggest the temperature may be closer to the higher end, nearly as hot as the surface of the Sun. This matters because temperature affects how quickly Earth is cooling and how long the geodynamo, the magnetic field generator, will last. Shockwave experiments also shed light on the mystery of light elements in the core. Seismology shows that the outer core is less dense than pure iron should be, meaning lighter elements like sulfur, carbon, or oxygen must be mixed in. By blasting iron alloys with different ingredients, scientists can measure how they behave under pressure. The results help narrow down which elements might really be present in Earth's heart. For example, recent experiments suggest that silicon and oxygen could account for part of the missing density, though other candidates remain possible. Studies of iron stages using shockwaves led to another big step forward. When things are normal, iron can be in a number of different crystal structures, but when it's under core pressure, it changes shapes. Experiments show that the iron in the inner core is arranged in a close-packed hexagonal pattern. In some situations, it may also form a body-centered cubic pattern. These changes in structure affect how earthquake waves move through the core, which helps explain strange things like anisotropy, which means that waves move faster in some directions than others. Lasers aren't the only thing used in shockwave studies. Gas guns are also used by scientists. These are machines that shoot bullets at metal samples at thousands of miles per hour. Shockwaves are made by the collision that feel like the pressure in the deep Earth, but they are cooler than lasers. Charges that explode have also been used to squeeze bigger samples for longer periods of time. Each technique gives you a unique perspective, and when you use them all together, they make a powerful set of tools for exploring the unseen. One challenge with these tests is the timescale. The extreme conditions exist for only nanoseconds, making measurements incredibly difficult. But advances in ultra-fast detectors and X-ray imaging now allow researchers to watch the behavior of atoms in real time. At facilities like the European X-ray free electron laser, pulses of X-rays just trillionths of a second long can capture snapshots of shocked materials, revealing how their crystal structures shift under pressure. This technology is opening an entirely new window into Earth's core physics. Shockwave studies are useful in more places than just Earth. They also help scientists figure out what's going on inside other worlds. Jupiter and Saturn, for instance, have metallic hydrogen, which is hydrogen that is squished so tightly that it acts like a metal. This strange state was made by shockwave tests on hydrogen in labs, which supports ideas about the magnetic fields of gas giants. Exoplanets are worlds that are bigger, heavier, and have even more extreme cores than Earth. The same kinds of tests can be done on them with iron and nickel. The temperature question. How hot is the center of Earth? Even though it seems like an easy question, experts have been trying to figure it out for over 100 years. The temperature at the heart of the Earth is so high that no thermometer could ever live there. To make predictions, scientists have to use a mix of indirect data from things like seismic waves, computer models, and lab tests. Over time, those figures have changed a lot, going from about 4,000 degrees Celsius to almost 7,000 degrees Celsius, which is about the same temperature as the Sun's surface. The exact answer is important because the Earth's core temperature affects how it changes over time, how its magnetic field works, and how long it can stay geologically active. The first clues about core temperature came from studying how heat moves through rock. Earth loses energy into space every day, radiating heat from its surface. Some of that heat comes from the crust and mantle, but a significant portion is thought to rise from the core. By estimating Earth's total heat flow and comparing it to what we see on the surface, scientists can calculate how hot the core must be to sustain this energy transfer. Early estimates suggested a relatively modest core temperature of around 4,000 degrees Celsius, hot enough to keep iron molten but cooler than modern measurements suggest. A second line of evidence comes from seismic studies. When seismic waves from earthquakes travel through Earth, they change speed depending on the density and stiffness of the material they pass through. To match the observed speeds in the inner and outer core, models of iron under pressure must be tested. The stiffness of the inner core implies that it is solid iron, but the exact wave speeds hint that its temperature is much closer to the melting point of iron at those extreme pressures. That puts the inner core's temperature much higher than early models predicted. This is where shockwave experiments and diamond anvil cells come in. By squeezing tiny samples of iron between two diamonds and then heating them with powerful lasers, scientists can simulate pressures and temperatures similar to those near the core. These experiments have shown that iron melts at around 6,000 to 7,000 degrees Celsius under core conditions. This suggests Earth's outer core is indeed molten at similar temperatures, while the inner core is just solid enough to resist melting, balanced right on the edge. Some studies say that iron's melting point is lower at those temperatures, while others say it is higher. The disputes happen because it's hard to make the lab settings so extreme again. It's hard to keep the heat and pressure steady for even a few seconds, and the effects rely on the method used. This is the reason why two science studies may still give various answers to the same question. The abundance of light elements in the core is another thing that makes the temperature debate more difficult. If the core were made of pure iron, it would be easy to describe how it works. But seismology tells us that it must also have smaller amounts of carbon, oxygen, silicon, or sulfur. The melting point of iron alloys can drop by hundreds of degrees when these elements are present. The expected temperature of the core can change a lot, depending on which elements are used in the estimates. Why does this matter so much? The answer lies in the geodynamo, the mechanism that powers Earth's magnetic field. The dynamo depends on heat flowing out of the core into the mantle. If the core is too cool, convection slows, and the magnetic field weakens. If it is hotter, convection is more vigorous, and the field stays strong. Knowing the core's temperature helps scientists predict how long Earth's magnetic shield can last. If the field collapses in the distant future, Earth would be left vulnerable to solar radiation, much like Mars, which lost its magnetic field billions of years ago. Temperature also affects how quickly the inner core is growing. As Earth cools, more of the liquid outer core solidifies onto the inner core, releasing heat and light elements that drive convection. If the temperature is closer to 7,000 degrees, the inner core may be younger, perhaps forming only 1 billion years ago. If it is closer to 4,000, it may be much older. This difference changes our understanding of Earth's history and the timeline of its habitability. We keep getting better predictions as new methods come out. Geoneutrinos are tiny particles that are released when radioactive elements break down inside Earth. They are studied to find out how much heat the planet makes from radioactive elements. These readings, along with surface heat flow data, help narrow down how much heat must come from the core which in turn tells us how hot it is. Looking at explosive fumes is another way to do it. Some gases, like helium-3, may come from deep sources close to the barrier between the core and the mantle. They may carry information about temperature to the surface. A fascinating new area of study is the use of synchrotron X-rays at places like the European Synchrotron Radiation Facility. Scientists can see how the atomic structures of iron alloys change by exposing samples to very strong X-rays while they are under pressure. Older tests had some problems that these studies are trying to fix. They point to a hotter, more sun-like core temperature. The age of the inner core. The solid center of Earth is about 3,200 miles below our feet. It is a thick ball made mostly of iron that is about 1,500 miles across. How old is it, though? How long ago did it form? It crystallized almost 4 billion years ago, but is it a much newer trait that formed only about 1 billion years ago? It's not a small thing. We can learn a lot about Earth's cooling past, its magnetic field, and even the conditions that made life possible by finding out how old the inner core is. The difficulty comes from the fact that we cannot see the core directly. Instead, scientists must infer its age from indirect clues: seismic wave behavior, computer simulations of heat flow, and laboratory experiments on how iron behaves under extreme pressure. These methods do not always agree, which is why estimates for the inner core's birth still range widely. The Earth's magnetic field is one of the most important pieces of proof. The magnetic shield is driven by convection in the liquid outer core. The heat leaving the inner areas keeps the outer core moving. As the inner core started to form, it sent more heat and lighter particles into the outer core, which made convection stronger. This would have made the motor stronger. Earth's magnetic field has been around for at least 3.5 billion years, but its strength and steadiness have changed over time, according to geologists who study old rocks. There is some evidence that the field suddenly got much stronger around 1 billion years ago. This may have been the start of inner core hardening. The study of earthquakes is another source of proof. Waves moving through the inner core don't always act the same way. In fact, they move more quickly from north to south than from east to west. This is known as anisotropy. This means that the iron crystals inside the core have likely grown and gotten more aligned over time. Some models say that the crystals would have to move billions of years to get where they are now, which suggests that the inner core is older. But newer models show that the process might be able to happen faster, which supports the idea that the inner core is younger and formed more recently. Heat flow is another crucial factor. Earth has been cooling since its violent birth, but the rate of cooling is not fully known. Laboratory studies of iron under core pressures suggest it conducts heat very efficiently. If true, the planet would lose energy faster than once thought, meaning the inner core could only have solidified relatively recently, perhaps around 1 billion years ago. On the other hand, if the core's conductivity is lower, it could have formed much earlier. This debate has even sparked questions about the survival of Earth's magnetic field. If the inner core is young, what powered the geodynamo before it began crystallizing? One possibility is that chemical convection drove the dynamo in the early Earth, with radioactive elements in the core releasing heat. Another idea is that the mantle above the core cooled unevenly, drawing out enough heat to keep convection going. Either way, the start of the inner core may have been a turning point that stabilized Earth's magnetic field for the long haul. Some seismic studies show that there is a inner core, a separate area in the middle that might have a different crystal structure or orientation. This could mean that the inner core formed in 2 steps. The first seed may have formed about 3 billion years ago, and it has been growing quickly over the last billion years. This 2-stage growth could make the old and young age models work together. The geologic record also provides indirect hints. Ancient zircons, tiny crystals found in rocks more than 4 billion years old, show evidence of a magnetic field at that time. If Earth's dynamo was already running so early, then some process other than inner core growth must have been powering it. This supports the younger age model, where the inner core is a later addition rather than an original feature of Earth. Paleomagnetism is the study of magnetic minerals in rocks from long ago. New discoveries are showing how strong the field was at different times. Some data point to a big change in strength around 1 billion years ago, which fits with the idea of a young core. At the same time, high-precision seismic studies are making more detailed maps of the inner core to look for signs of crystal growth patterns that could tell us how old it is. Helium from the deep. Helium is in every breath you take, but not the kind that comes from deep inside the Earth. Most of the helium we use in balloons and medical equipment is helium-4, which is made when radioactive elements break down in the ground. Helium-3, a light isotope that has stumped scientists for decades, is much less common. Helium-3, on the other hand, is thought to be primordial. It is something that was left over when Earth was being formed and has been stuck inside the planet ever since. We sometimes get a short signal from deep inside the Earth, maybe even from the core, when we smell helium-3 rising through volcanic fumes. Helium-3 is precious because it acts like a tracer gas. It doesn't chemically react with other elements, so if we detect it at the surface, it means it traveled unaltered all the way from its source. The key mystery is where exactly inside Earth it hides. Some researchers believe large reservoirs exist near the core-mantle boundary, locked away since Earth accreted from the solar nebula 4.5 billion years ago. Others argue it is mostly stored in the mantle, seeping upward over time. The evidence comes from volcanoes. Certain volcanic hotspots, such as those in Hawaii and Iceland, emit helium-3 at higher ratios, compared to helium-4, than ordinary mid-ocean ridges. These helium signatures suggest that plumes rising from deep inside the mantle are tapping into reservoirs that haven't been stirred or mixed much since Earth's early days. The hotspots may be tapping directly into a primordial helium pocket, lying just above the core. The presence of helium-3 ties directly to the question of Earth's origin. If the gas is indeed from the solar nebula, the same cloud that formed the Sun and planets, then parts of Earth's deep interior have remained isolated for billions of years. This isolation challenges the idea that mantle convection has fully mixed the planet's interior. Instead, it suggests some hidden reservoirs of ancient material remain untouched, like time capsules of the early solar system. Some fresh analysis even suggests that some helium-3 might come from the core itself. Scientists found an extremely high amount of helium-3 in volcanic fumes from Baffin Island in 2022. This island is thought to be connected to deep mantle plumes. The only source that made sense to them was a reserve close to the border between the core and the mantle. We could have a direct biochemical link between the Earth's surface and its heart if this is true. For billions of years, the core has been slowly losing helium-3. But how could helium stay alive in the center? Helium is hard to trap in iron, which is the main part. One theory says that helium mixed with the liquid metal when Earth was being formed, when big impacts, like the one that made the Moon, heated the planet very much. Some helium may have been pushed out of the core as it solidified and into the mantle above. It stayed there until mantle plumes brought it to the surface. The discovery of helium-3 also plays a role in understanding Earth's cooling rate. If helium is escaping today, it implies that reservoirs are slowly emptying. By measuring the total flux of helium-3 into the atmosphere, around 2,000 grams per year, scientists can estimate how quickly Earth is losing its primordial inventory. The numbers suggest that Earth still contains vast amounts of helium-3 inside, but only a tiny fraction leaks out each year. Helium-3 has also captured attention beyond geology. In the energy world, helium-3 is considered a potential fuel for fusion reactors. It could, in theory, produce clean energy without dangerous radioactive byproducts. This is one reason space agencies talk about mining helium-3 from the Moon, where it has accumulated in the soil over billions of years thanks to the solar wind. But the rare helium-3 leaking from Earth's core is a reminder that our own planet still holds hidden stores of this exotic element. Tracking helium-3 is difficult. It is so rare, just one atom of helium-3 for every million atoms of helium-4, that highly sensitive mass spectrometers are needed to detect it. Geologists collect gas samples from volcanic vents, geothermal springs, and even trapped bubbles in rocks. Every new detection helps refine the map of helium-3 sources, painting a picture of Earth's deep plumbing system. That helium-3 might be connected to other noble gases like neon and argon, which also show strange things in deep plumes, is one of the most intriguing speculations. They might make up an elemental fingerprint of the deep Earth when put together. Scientists can tell the difference between gases rising from untouched, old reserves, and gases recycled from the crust by comparing the ratios of helium-3 to other isotopes. The geodynamo's future. Deep below our feet, the magnetic field that protects Earth from dangerous sun radiation is made by swirling currents of molten iron and nickel in the Earth's outer core. For billions of years, this unseen force called the geodynamo has kept Earth safe by blocking charged particles and stopping the atmosphere from being stripped away like it did on Mars. But it's not certain that the geodynamo will last forever. It's possible that the magnetic shield will weaken or even fall apart at some point, because the Earth's core will cool down. How long do we have? That's the big question. The geodynamo depends on movement. Right now, convection in the outer core is driven by two main processes: heat escaping from the inner core as it slowly cools, and lighter elements like oxygen and sulfur being released as the inner core crystallizes. Together, these processes stir the molten metal and set it into motion. Combined with Earth's rotation, the flow creates a self-sustaining magnetic field. But as Earth ages, its internal heat budget changes, and the efficiency of this dynamo changes with it. Some scientists think Earth's geodynamo could remain active for billions of years into the future. The inner core is still relatively young, perhaps only 1 to 1.5 billion years old, which means plenty of heat and chemical energy remain to drive convection. If this is correct, Earth may continue to enjoy a strong magnetic field long after other processes on the surface, like plate tectonics, have slowed down. Some people are worried that the field is already becoming unstable. The Earth's magnetic field has gotten weaker by about 10% in the last 200 years. A huge area called the South Atlantic Anomaly has become much thinner, which makes satellites not work properly as they pass through it. Some see this as proof that the geodynamo is changing, maybe getting ready for another magnetic shift where the North and South poles switch places. Earth's history is full of reversals. The most recent one happened 780,000 years ago. However, we still don't fully understand what causes them. The Earth might be hit with more sun energy if the field weakens too much. Even though our environment would still protect us, satellites, power lines, and modern technology would be at risk. Even animals that use the magnetic field to find their way, like birds, whales, and turtles, could be harmed. What will happen to the geodynamo in the end is not just a natural question. It is also a question about the survival of technology and life on the surface. To predict the future, scientists turn to models of core cooling. Right now, Earth loses about 40 to 45 terawatts of heat into space, a fraction of which comes from the core. If that cooling continues at the current rate, the inner core will keep growing, releasing heat and light elements that fuel convection. That could keep the dynamo alive for at least another billion years. But if the core is more efficient at conducting heat than we think, convection may slow sooner, possibly shutting down within a few 100 million years. It's interesting to think that the geodynamo might not just turn off all at once. Instead, it might get weaker, stutter, and then get better in loops. This might be going on right now. Some studies of paleomagnetism show that the field has had times when it was weak and quickly changed direction, followed by times when it got stronger again. Changes like these could mean that the geodynamo is stronger than thought and can fix itself even as the core changes. Other worlds give us sobering comparisons. Mars once had a magnetic field, likely powered by a molten core, but it shut down about 4 billion years ago when the planet cooled too quickly. Without its magnetic shield, Mars lost most of its atmosphere to space, leaving behind a barren desert. Mercury, on the other hand, is much smaller than Earth, but still has a weak magnetic field, perhaps maintained by unusual sulfur chemistry in its core. These planetary case studies remind us that Earth's geodynamo is not inevitable. It is a delicate balance of size, heat, chemistry, and rotation. Comparing Earth and Mars. Because Earth and Mars are both hard and formed from the same solar nebula about 4.5 billion years ago, they are often called brothers. But now they don't look anything alike. There are oceans, woods, and a magnetic screen that keeps the atmosphere in place on Earth. Mars, on the other hand, is cold, dry, and empty, and its thin atmosphere can't protect it from the sun's winds. The guts of the two are one of the most obvious ways they are different. The geodynamo that keeps Earth's magnetic field going is still powered by the core's heat, liquid, and convection. On the other hand, Mars's core has cooled and hardened, so it no longer has a magnetic field around it. One of the biggest mysteries in orbital science is why Earth is doing so well while Mars is not. Billions of years ago, Mars wasn't so lifeless. Evidence from ancient river valleys, deltas, and lake beds shows that it once had flowing water and possibly even oceans. For this to be possible, it must have had a thicker atmosphere to trap heat and keep water liquid. Scientists believe Mars once had a magnetic field, generated by a molten core much like Earth's. The magnetic shield would have protected the atmosphere from being stripped away by solar radiation. But around 4 billion years ago, the Martian dynamo died. Without protection, solar winds gradually blew the atmosphere away, transforming the planet into the cold desert we see today. The reason for this divergence lies in planetary size and heat retention. Earth is larger, with a radius of about 3,959 miles, compared to Mars's 2,106 miles. That extra size means Earth's core retains heat far more effectively. Mars, being smaller, cooled much faster. Its outer core likely solidified early, shutting down convection and halting the geodynamo. Without a molten, churning metal core, Mars could no longer generate a magnetic field strong enough to shield its atmosphere. Chemistry may also play a role. Studies suggest Mars's core is rich in sulfur, which lowers the melting point of iron. This might have allowed the core to remain molten for a time, but not vigorously convecting enough to sustain a strong dynamo. Eventually, as the core cooled further, convection weakened to the point of collapse. Earth's core, by contrast, contains a balance of light elements like oxygen, silicon, and sulfur that may have helped sustain convection longer. Seismic studies of Mars, particularly from NASA's InSight mission, have shed new light on this mystery. InSight detected Mars quakes that allowed scientists to probe the planet's interior. The results suggest that Mars still has a liquid outer core, but it may be partially stratified, with a stable layer at the top preventing vigorous convection. If true, this would explain why Mars no longer generates a magnetic field. The molten metal may still exist, but it isn't moving in the right way to drive a dynamo. Earth also benefits from an additional energy source, the slow crystallization of the inner core. As the inner core solidifies, it releases heat and lighter elements into the outer core, fueling convection. Mars may never have reached the point of forming a solid inner core, or if it did, the process was too weak to sustain the dynamo for long. This difference may have given Earth's dynamo a second wind, while Mars's simply flickered out. There are huge effects from this difference. Earth kept its atmosphere and seas because its magnetic shield was still in place. This made for a safe climate where life could grow. Mars lost most of its surface water when it lost its atmosphere. It is no longer a place where life as we know it could exist. Water is now only found in small amounts as ice at the poles and in deep sources. Mars might still be a live world with lakes, rivers, and maybe even forests if it had kept its magnetic field. Seeing how Earth and Mars are alike can also help us figure out what will happen to Earth in the future. Just like Mars's dynamo died, Earth's will finally go out as its core cools down. It's not clear when it will happen. It could be billions of years. But when it does, Earth will have the same problems. Its shield will be weaker, its atmosphere will be more exposed, and it will slowly change. Looking at Mars is like looking into the far future of Earth. It serves as a warning that our magnetic field is not permanent. This similarity can also be seen from the point of view of the chance of life. As long ago as billions of years ago, Mars may have had life on it if it had a magnetic field and a thick atmosphere. The rovers from NASA are still looking for biosignatures in old rocks. They want to find proof of microbes that lived on Mars during its short period of habitability. At least 3.5 billion years ago, life began on Earth. Around the same time, Mars lost its engine. It's possible that life could have grown on Mars as well if it had kept its core-generated screen in place a little longer. Core quakes. When most people hear the word earthquake, they think of cracks moving in the rock, which causes buildings to shake, mountains to crack, and tsunamis to form. But not every earthquake happens close to the ground. Some happen in the Earth's core, thousands of miles below the surface. Core quakes are what these things are, and they are still one of the most mysterious things in science. Core quakes seem to come from the inner core, which is a solid sphere of iron and nickel that is under crushing pressures and burning heat. Surface quakes are caused by the movement of tectonic plates. Detecting core quakes is no easy task. They do not produce the same kind of obvious seismic signals as shallow quakes. Instead, scientists look for tiny distortions in the way seismic waves travel through Earth. When a large earthquake occurs on the surface, the shock waves spread through the entire planet. On their way, they pass through the core. Sometimes, these waves appear to scatter, speed up, or even bounce differently than expected. The subtle anomalies hint at activity within the inner core, almost like listening to faint echoes from a hidden world. There are many questions about the idea of quakes in the core. For example, how can a solid ball of iron that has been pressed to a very high density quake? It's possible that the iron cells that make up the inner core change shape and grow over time, letting go of stress in short bursts. Picture ice growing on a pond. As it changes, the ice cracks loudly from time to time. It's possible that the inner core is doing the same thing, but at pressures more than 3 million times higher than the air at sea level. Some seismic studies have shown evidence of sudden changes in wave speed deep within the inner core. These abrupt shifts could represent localized slips in iron crystal alignment, similar to tectonic slips in the crust. If so, core quakes are essentially deep, iron-based versions of earthquakes. Only instead of rocks grinding against one another, it is giant metallic crystals shifting under unimaginable stress. What makes core quakes particularly fascinating is their potential link to Earth's magnetic field. If the inner core wobbles or shifts, it could influence the flow of molten metal in the outer core, which drives the geodynamo. Some scientists speculate that irregularities in the magnetic field, such as the drifting of the magnetic North Pole, might be tied, at least in part, to movements within the inner core. Core quakes could be tiny pulses of energy that ripple outward, nudging the dynamo above. When scientists looked at faraway KPP seismic waves, a type of wave that moves through the deep core, they found something very interesting. Sometimes these waves come in earlier or later than predicted, which suggests that the inner core is not perfectly flat. In fact, it might have patches of slightly different densities all over it, like a patchwork. Some of those patches could cause what we call core quakes if they move quickly. In 2018, researchers reported intriguing evidence of a possible inner core quake that seemed to alter the speed of waves for years afterward. It was as if a fracture or reorganization had occurred deep inside, leaving a long-lasting scar detectable by sensitive instruments. Though still debated, such findings suggest the inner core is far more dynamic than once thought, not a static ball of iron, but a living, shifting structure with its own seismic life. The study of core quakes is still in its infancy. Seismologists rely on the largest earthquakes at the surface to probe the deep Earth. because only the strongest events send waves powerful enough to reach the core. Each time a magnitude 8 or 9 earthquake shakes the crust, scientists eagerly analyze the seismic data, searching for hints of deep anomalies. Slowly, they are building a picture of what happens in the heart of the planet. Exotic core theories. People thought that the center of the Earth was a simple ball of liquid iron for hundreds of years. Scientists now know it's a lot stranger and more complicated than that picture shows. Inside, the core is solid, and outside, it's liquid. The two together make the geodynamo that drives our magnetic field. But the more scientists look, the more they find that the core may have strange states of matter that make our understanding of physics harder to grasp. People used to think these ideas were just crazy theories, but now they're becoming more popular as tests, computer models, and seismological studies find strange options 4,000 miles below our feet. The idea of superionic hydrogen in the deep Earth is one of the most attractive ones. H+ atoms act in this strange state like they are a mix of a liquid and a solid. The structure of oxygen and iron stays stiff, but the hydrogen ions can move around easily, kind of like how water flows through a crystal. This state of matter has been proven by lab tests that mimic the conditions inside big planets like Neptune and Uranus. Now, some scientists are wondering if there might also be a thin layer of superionic hydrogen near the boundary between Earth's core and mantle. This layer could change the way heat and electricity move in that area. If it's true, it might change the magnetic field and even help explain some strange earthquakes. The idea of iron snow is another peculiar idea. This idea says that the outer core might not be a smooth ocean of molten iron. Instead, little iron crystals could form and snow down onto the heart. This slow, heavy rain would send heat and lighter elements into the liquid core's upper layer, which would fuel convection and power the generator. New computer models show that this process might be going on right now, mainly at the very top of the outer core. If there is iron snow, it would change the way we think about the flow of energy inside the Earth. There is also evidence that the core may contain strange alloys not found anywhere else. While iron and nickel dominate, seismic data suggests that lighter elements such as carbon, silicon, sulfur, or even oxygen are mixed in. But at the extreme pressures of the core, over 3 million times atmospheric pressure, these elements may not behave like they do on the surface. Some models suggest that exotic compounds could form, with unusual crystal structures never seen before in laboratories. These alien materials might explain why seismic waves travel unevenly through the core, or why parts of the inner core seem softer than expected. Perhaps the inner core is not a solid sphere, but rather patches of semi-molten rock. This is another bold idea. Seismic imaging has shown places where waves move more slowly, which could mean that the ground is softer or partly melted in those places. Some parts of the inner core might really be gooey, which would mean that Earth's deepest layer is not smooth, but a mix of solid, semi-solid, and crystalline styles. This might also help explain why the inner core of the planet seems to spin a little differently than the rest of the planet. Some researchers go further and suggest that the inner core could host a superionic iron state, where iron itself takes on strange properties at extreme temperatures. Instead of behaving like an ordinary solid, the iron lattice could vibrate intensely, allowing atoms to move in ways that defy surface-based physics. If such a state exists, it could make the inner core partially behave like both a metal and a liquid at the same time. This would revolutionize our understanding of conductivity and heat transfer in Earth's deepest regions. There is also the idea of hidden layering within the core. Seismic studies have hinted at a possible inner core, a smaller sphere within the inner core that has different crystal alignment or composition. If true, this layered structure would suggest that Earth's inner heart has changed over time, recording different stages of the planet's cooling history. Some scientists even speculate that the inner core could be a relic of Earth's earliest days, preserving chemistry from a time before plate tectonics even began. Experiments in the lab keep pushing the limits of what we think we know. Scientists can heat and press small pieces of iron to thousands of degrees and millions of atmospheres using huge laser arrays. For fractions of a second, these shockwave tests mimic core conditions. This lets experts look into how matter acts at those very high and very low temperatures. Some data show that core iron is much lighter than expected, while others show that it conducts electricity in a way that is not typical. These results make it possible for matter to be in states that were not thought possible before. The inner core. In the 1930s, when scientists first found Earth's inner core, they thought it looked like a simple solid iron sphere. Seismic studies over the years have shown a lot of surprising complexity, including anisotropy, uneven growth, and hints of strange stages of matter. But one of the most surprising discoveries in the past few years is that the inner core might have a smaller disk inside it that is different from the rest of the inner core. It's like Earth's heart has another heart inside it. The first hints came from seismic data. When seismic waves pass through Earth, they travel at different speeds depending on direction. This phenomenon, called anisotropy, revealed that the inner core's iron crystals are aligned more strongly along Earth's rotation axis than along the equator. But around 20 years ago, researchers noticed something odd. Waves traveling through the very deepest part of the inner core behaved differently than those passing through its outer layers. It was as though they were crossing into a region with a different crystal structure or orientation, a sphere within a sphere. This inner core is thought to be about 400 miles across, which is about half the size of the Moon. It could have crystals that are not aligned the same way as the rest of the inner core. When you get to the edge of the inner core, earthquake waves move fastest from north to south. But inside the inner core, the fast movement doesn't seem to be going in the same direction as Earth's spin. The deepest part of the inner core may have formed under different conditions than the rest. Why would Earth have such a structure? One explanation is that the inner core records an ancient transition in Earth's history. Perhaps when the inner core first began to solidify, it crystallized in one alignment. Later, something changed. Maybe the growth pattern shifted, or the rotation of the core altered slightly, causing the newer layers to crystallize differently. In this sense, the inner core could be a time capsule, preserving a chemical and structural snapshot of Earth's earliest dynamo activity. The inner part of the inner core might also be made of different materials than the upper part of the inner core. If more light elements like carbon or silicon were caught when it was first being formed, the crystal structure might be different from the iron-rich layers around it. This might also help explain why earthquake waves move through the deepest core and change speed, or slow down in unpredictable ways. Computer simulations support the idea that iron can take multiple crystal forms under extreme pressure. At core conditions, iron may adopt a hexagonal close-packed HDP structure, but under slightly different conditions, it might flip into a cubic structure. If the innermost region crystallized under one phase and the outer inner core under another, it could explain the seismic anomalies. In effect, the inner core may represent a buried fossil of an earlier phase transition. The idea of an inner core also raises questions about the timing of Earth's magnetic field. If the deepest core crystallized differently, it may mark the birth of Earth's geodynamo. Some researchers suggest the inner core is only about 1 billion years old. If so, the inner core could preserve the moment the dynamo first switched on, when the release of heat and light elements began powering the magnetic field we still rely on today. The discovery is still debated because the seismic signals are faint and difficult to interpret. Only the largest earthquakes send waves strong enough to pass through the very center of the Earth and back. Even then, the signals must be carefully filtered to distinguish them from noise. Despite these challenges, multiple studies over the past 2 decades have found evidence pointing to the same conclusion. The innermost 400 miles of Earth's core are different from the rest. Planetary formation clues. The Earth's core may be the most important record of everything that shows how it was formed. The core is buried under more than 4,000 miles of rock and metal. It keeps chemical fingerprints and temperature patterns that date back to the wild days when our planet was first formed. The top has been changed many times by weathering, plate tectonics, and living things, but the core has stayed sealed and hidden. It's like a time capsule because it holds secrets about Earth's rough childhood and how it changed from a cloud of dust to a live world. About 4.6 billion years ago, the Sun formed from a collapsing cloud of gas and dust. The leftovers, small rocky chunks called planetesimals, collided and merged to create the rocky planets, including Earth. These collisions generated enormous heat, enough to melt the young planet. Heavy elements like iron and nickel sank to the center, while lighter materials floated upward to form the crust and mantle. This process, called differentiation, produced the layered structure we see today. But the exact details of how quickly Earth's core formed and what elements it trapped remain subjects of intense study. One of the strongest clues comes from isotopes, the slightly different versions of elements. Certain isotopes of tungsten and hafnium, for example, provide a clock for dating core formation. The ratio of tungsten 182 to hafnium 182 in rocks suggests that Earth's core formed extremely quickly, within the first 30 million years of the planet's history. This rapid segregation of metal and rock may have been triggered by colossal impacts, including the giant collision that likely created the Moon. If so, the core we know today could contain not only Earth's original metal, but also material from alien worlds that struck us during those fiery times. Even helium-3, a rare isotope, offers a planetary birth certificate. Helium-3 is thought to be primordial, trapped during Earth's formation from the solar nebula. Today, small amounts escape from volcanic plumes, suggesting reservoirs deep inside, possibly near the core-mantle boundary. If so, Earth's interior may still hold gases that predate the planet itself, a direct whisper from the time before worlds existed. The inner core also records the thermal history of Earth, how quickly it crystallized, how it grew, and how heat escaped, all tied back to the planet's early cooling. Some studies suggest that the inner core may have only started forming about 1 billion years ago, long after Earth's birth. If true, then for most of Earth's history, the core was entirely molten. That raises questions about how the geodynamo, our magnetic field generator, functioned in earlier times. Perhaps radioactive elements or compositional layering provided the needed energy until the inner core began to solidify. Either way, the growth of the inner core marks a turning point in Earth's evolutionary story. There are also seismic hints that the inner core, a distinct sphere within the inner core, may preserve even older signatures of Earth's formation. Its unusual crystal alignment could reflect conditions during the earliest phase of core solidification, possibly capturing the moment when the geodynamo first ignited. If confirmed, this would mean Earth's deepest center contains a fossil record written in iron crystals, stretching back billions of years. Experiments on metallic alloys at extreme pressures provide further insight. By squeezing mixtures of iron, nickel, and lighter elements to millions of atmospheres, scientists simulate conditions in the core. These experiments reveal which compounds remain stable, which melt, and how they might have separated during Earth's infancy. The results suggest that early Earth may have gone through multiple differentiation stages, with metals sinking not just once but in waves, each leaving chemical fingerprints. The core and life. The trees, animals, and people that live above seem to have nothing to do with something that is 4,000 miles below the surface. Still, Earth's core has been very important in making life possible. Without the inner and outer cores, Earth would be a barren, hostile world without seas or atmosphere that is constantly hit by dangerous radiation from space. One of the most interesting stories in Earth science is about the connection between the core and life. For billions of years, the beating iron heart at the center of the planet has been the silent guardian of life. The most direct connection comes from Earth's magnetic field. Generated by the geodynamo in the outer core, this invisible shield stretches far into space, forming the magnetosphere. Without it, solar wind, charged particles streaming constantly from the sun, would strip away our atmosphere. That is exactly what happened to Mars. Once, Mars had a magnetic field and surface water. But when its smaller core cooled and stopped convecting, the magnetic field collapsed. With no protection, the solar wind slowly eroded the Martian atmosphere, leaving behind a dry, frozen desert. Earth avoided that fate because its core stayed molten and active. This shield does more than hold the air in place. It also protects life from cosmic radiation. High-energy particles from the Sun and from beyond the solar system are deflected by the magnetosphere. Without this barrier, radiation would bombard the surface, making it much harder for complex organisms to survive. In fact, the magnetic field funnels particles toward the poles, creating the auroras, beautiful, glowing reminders of the shield that protects us every day. The core also influences the long-term stability of Earth's climate. By generating the magnetic field, it prevents the loss of greenhouse gases like carbon dioxide and water vapor. These gases are essential to keeping Earth warm enough for liquid water and life. If Earth's core were to shut down and the magnetic field disappear, the atmosphere would slowly leak into space, and Earth could eventually resemble Mars, cold, dry, and lifeless. Plate tectonics is powered by convection in the mantle, which is caused by heat leaving the core. Volcanoes, earthquakes, and mountain ranges are all made by the ongoing reworking of crustal material. Plate tectonics has been very important for life's long-term survival, even though it is damaging in the short term. Volcanic outgassing adds carbon dioxide to the air, and subduction pulls carbon-rich rocks back into the mantle. Over millions of years, this cycle keeps Earth's temperature stable, stopping greenhouse effects from getting out of hand, like they do on Venus, or total freezing, like they do on Mars. There is a straight link between the core's heat and keeping conditions that are good for life. There is also proof that the core has had surprising effects on the development of life. During magnetic reversals, the poles switch places. Earth's field gets weaker for a short time. More cosmic radiation gets to the surface at these times. Radiation bursts during reversals may have swayed evolutionary paths and may have even caused DNA changes, according to some scientists. This is still being discussed, but it shows how deeply connected the processes happening deep inside the Earth are to the story of life on the surface. The core also leaves a signature in some of life's earliest records. Ancient rocks more than 3 billion years old show traces of magnetism frozen in as they formed. These fossil magnets prove that Earth's magnetic field has existed for nearly as long as life itself. This suggests the core's dynamo was already active when the first microbial ecosystems emerged. Life and the core, then, may have grown together, one shielding and sustaining the other. Life may also give us clues about the core in a roundabout way. Some isotopes of noble gases, like helium-3 and xenon, have been found in volcano plumes. This suggests that gases from Earth's early days are still stored in reserves close to the border between the core and the mantle. These isotopes were not made by current methods. They are leftovers from when the planet was first formed. Their escape through volcanoes gives us rare signs about what lies at the deepest limits, which connects biology and geology in ways we didn't expect. When we look at Earth in light of other worlds, the role of the core becomes even more clear. For example, Venus is about the same size and makeup as Earth, but it doesn't have a strong magnetic field. Its core might not be convecting because it doesn't have plate tectonics to cool it down well. Without a cover to protect it, Venus's thick atmosphere turned into a greenhouse that got out of hand, heating the planet to 900 degrees. It's been a long time since Mars's core generator was turned off, leaving it open and dead. Earth was the only one that was the right size to keep heat in, busy enough to keep the dynamo going, and big enough to recycle its atmosphere and seas. This delicate balance shows why the search for life on exoplanets often includes questions about their cores. Astronomers know that habitability depends not just on being the right distance from a star, but also on having a magnetic field to guard against radiation. Without an active core, even a planet with oceans and air might lose them within 1 billion years. In this sense, Earth's core is not just a geological feature, it is a biological requirement. The limits of exploration. We can't even get to the Earth's core, which is about 4,000 miles below us. It might as well be in another world. People have walked on the moon, sent robots beyond the solar system, and made very detailed maps of Mars's surface. But we still can't reach the center of our own world. The problem isn't a lack of desire. Scientists and engineers have long wanted to go deeper, but the physical obstacles that make reaching the core one of the most impossible things in science. The deepest humans have ever drilled is the Kola super deep borehole in Russia. Work began in the 1970s, with the goal of reaching 9 miles down into the crust. After 2 decades, the project was abandoned. Engineers managed to drill 7.5 miles, just a fraction of the way through the crust, and less than 1/3 of 1% of the distance to the core. The deeper they drilled, the more problems they faced. The rock behaved more like plastic than stone, squeezing the drill hole shut. Temperatures soared to 350 degrees Fahrenheit, far hotter than expected, warping and destroying equipment. If just 7 miles down posed such obstacles, imagine the difficulties at thousands of miles. The temperature and pressure in the core are staggering. At the outer core, pressures reach more than 3 million times Earth's surface air pressure, and temperatures are estimated between 7,000 and 9,000 degrees Fahrenheit, comparable to the surface of the Sun. No material humans can create would survive those conditions. Steel, titanium, even diamond would melt or shatter long before reaching those depths. Drills would warp, electronics would vaporize, and protective casings would collapse under the weight of the planet itself. Even if materials could withstand the conditions, the scale of the journey is overwhelming. The core begins 1,800 miles down, and the inner core sits at 3,200 miles. Moving equipment through solid rock for such distances is beyond any current or even foreseeable technology. For comparison, building a tunnel to the core would be like digging a road that stretches 500 times deeper than Mount Everest is tall. Some have proposed unconventional approaches. Ideas include using nuclear explosions to fracture the crust and mantle, then sending instruments through the cracks, or deploying self-melting probes that would burrow by heat. But nuclear blasts would seal themselves with molten rock, while melting probes would cool and stall as heat escaped into the surrounding rock. Even the most imaginative science fiction-style plans collapse under the realities of physics and geology. Scientists use indirect methods instead of direct ones to explore. When an earthquake happens, it sends seismic waves through the Earth like X-rays. Scientists use the way these waves speed up, slow down, or bend to make maps of the Earth's layers. These maps show where the crust, mantle, outer core, and inner core meet. To touch the heart is better, but this is as close as we can get. Using lasers to blast samples or diamond anvils to press them down can also be used in the lab to simulate core conditions for fractions of a second. These show how iron and other elements act when they are under a lot of pressure. By keeping an eye on the magnetic field, which comes from the outer core, satellites add another level of study. As the field changes, so does the metal that is moving under our feet. Scientists get hints about how liquid iron moves by keeping an eye on how the field's strength and direction change over time. This turns the top of the Earth and space itself into views into the depths that can't be reached. This doesn't mean that research is over, though. Our tools get better as technology does. Computer models get clearer, lab studies get more accurate, and seismic networks get thicker. Some people even think that nanotechnology will one day make probes that are so small they can sink deep into the Earth and be moved along by natural convection currents while sending data back as they go. These are still just dreams, but they show how much we want to know. What is at the center of our world? What still lies unknown? Scientists have learned amazing things about the crust, mantle, and core after studying the Earth's innards for more than 100 years. Scientists have drawn maps of earthquake boundaries, measured how waves bend deep inside the Earth, and made labs that simulate the pressures of millions of atmospheres. Even with all of these improvements, the middle of the Earth is still one of the most puzzling places in science. There are more questions as we look further. Who or what is at the center of the world? What makes it what it is? How much do we really not know? The exact makeup of the heart is one of the biggest unknowns. Seismic tests show that it's mostly iron and nickel, but the density isn't quite right for a pure metal. In this case, smaller elements like carbon, sulfur, oxygen, silicon, or hydrogen are mixed in. What's unclear is which of these are present and how much of each there is. There are different effects of each option. If carbon is easy to find, then Earth's early world had a lot of organic molecules. If sulfur rules, then Earth's building blocks were more like some kinds of asteroids. We can only guess since we don't have direct samples. Solving this puzzle would not only help us understand how Earth formed, but it would also help us figure out how planets around other stars work. Another unanswered question is the true temperature of the core. Current estimates range from 7,000 to 9,000 degrees Fahrenheit, but these are based on models, experiments, and seismic interpretations. The difference may sound small, but in geophysics it changes everything, from how fast the core cools to how long the magnetic field will last. If the core is at the hotter end, Earth's geodynamo may remain active for billions of years. If it is cooler, the magnetic shield could weaken sooner than expected, with profound consequences for life. It's not even clear how old the inner core is. Early on, almost 4 billion years ago, or not long ago, about 1 billion years ago. This lack of clarity changes everything we know about how Earth evolved. If the inner core is old, then solidification has been the geodynamo's power source for most of Earth's past. If it is new, the magnetic field must have been powered by something else before it showed up. In the iron crystals, the real age is written, but we don't know how to read it yet. That which is unknown is how the inner heart acts. Seismic waves can show uneven growth, anisotropy, and even an inner core. The deepest area may represent a different phase of matter, but we still don't know why one hemisphere grows faster than the other. The thought that Earth's deepest center might have more than one layer inside layers shows a level of complexity that we are still trying to fully understand. The future of the geodynamo is also uncertain. Earth's magnetic field has flipped many times in the past, sometimes weakening drastically during reversals. Right now, we see unusual behavior in the South Atlantic anomaly, where the field is especially weak. Is this the beginning of another reversal, or just a temporary fluctuation? Will Earth's magnetic field remain stable for another billion years, or is it already in decline? Without knowing exactly how the core evolves, we cannot predict the shield's future with confidence. Even seismic probing, our best tool, has limits. Earthquakes send waves through the planet, but they only occur in certain places, and not always with the strength or geometry needed to illuminate the deepest layers. Our maps of the core are still blurry, with patches of uncertainty where data is scarce. It is like trying to understand the structure of a house by listening to echoes through the walls. The picture is partial and always open to revision. There are also tantalizing questions about the connection between the core and life. Did the timing of the core's solidification help stabilize Earth's climate, making it habitable for complex organisms? Do magnetic field reversals influence mutation rates and evolution? Could changes in the core even play a role in mass extinctions by altering the planet's shield against radiation? These questions straddle geology, biology, and astronomy, and remain far from settled. Some of the most speculative unknowns involve exotic states of matter. Experiments suggest that hydrogen may exist in a superionic state at core pressures, where ions move like a liquid, while electrons flow like a solid. If such exotic phases exist in Earth's core, they could dramatically change its properties, affecting conductivity, magnetism, and even how heat is transferred. We may never know for certain, but the possibility highlights how far we are from a complete picture. There's also the simple fact that no one will ever touch the heart. We can't send robots or humans there like we can to the Moon or Mars. Models, creative tests, and secondary measures will always be important to what we know. In other words, there will always be doubts, arguments, and puzzles. The core will always be a mystery to us. It is the last limit of our own world. We may never drill to the center of our world, but every earthquake, every magnetic flicker, every plume of volcanic gas gives us another glimpse into the heart beating 4,000 miles below. The Earth's core remains one of science's greatest mysteries, a place where answers shape not just our planet, but our survival. If you enjoyed this journey to Earth's hidden depths, make sure to like, subscribe, and share your thoughts in the comments. And join us again for more cosmic adventures here on Beyond Horizons.